Have you ever wondered why the simplest questions often unlock the deepest mysteries? From a barber who can't decide if he should shave himself, to a cat that is both alive and dead, to the terrifying possibility that reality itself might just be a simulation. Paradoxes force us to question everything we think we know. They aren't just riddles, they are doorways into the limits of logic, the strangeness of science, and the very meaning of existence. Each paradox is like a mirror held up to our minds, showing us where reason cracks and mystery begins. In this video, we'll journey through some of the most mind-bending paradoxes ever conceived, each one challenging the way you see truth, time, and reality itself. So, if you're ready to expand your mind and step into the impossible, stay tuned. And don't forget to like this video, subscribe for more deep explorations, and hit the bell icon so you never miss the next idea that just might change how you see the world. The barber paradox. Picture a quiet little town with one single barber. This barber is not just any ordinary man with scissors and a razor. He has a rule that defines his entire job. He shaves every man in the town who does not shave himself, and he never shaves a man who does shave himself. On the surface, this rule sounds neat and simple, almost like a perfectly balanced system. But when we look deeper, a strange and puzzling question emerges. Who shaves the barber? If the barber decides to shave himself, then by his own rule, he should not be shaving himself, because he only shaves the men who do not. But if he chooses not to shave himself, then he suddenly falls into the category of men who must be shaved by the barber, which means he must shave himself after all. Either way you try to solve it, you end up stuck in a contradiction that goes in circles. The moment you think you've solved it, the paradox flips back on itself and leaves you with no consistent answer. This is the essence of the barber paradox. It is not really about shaving or barbers at all. It is a clever way to show the limits of logic when a rule is applied to itself. It belongs to a larger family of puzzles known as self-referential paradoxes, where a statement or a rule breaks down the moment it tries to include itself within its own definition. Just like trying to chase your own shadow, the answer always slips away the closer you get. The barber paradox was made famous by the philosopher and logician Bertrand Russell, who used it to point out problems in the foundations of mathematics and logic. It revealed that certain systems, no matter how carefully designed, can collapse into contradiction if they allow rules to loop back onto themselves. The lesson is powerful. Sometimes, the problem is not in the answer, but in the way the question is asked. The barber paradox reminds us that some questions are built on flawed assumptions, and no matter how hard we try, they cannot be solved because the very structure of the problem contains the contradiction. In the end, the barber paradox is not just a riddle, it is a mirror held up to the way humans think. It shows us that language, logic, and rules have hidden traps when we push them to their limits. And that's why this simple story about a barber in a small town has fascinated thinkers for over a century, challenging us to see beyond surface-level simplicity and question whether all problems are even meant to have an answer. The liar paradox. At first glance, the liar paradox sounds almost too simple. Imagine someone saying, "This statement is false." Now, stop and think about it. If the statement is true, then it must be false, because it says it is false. But if the statement is false, then that means it is actually true. You're trapped in a loop where neither answer works, and every time you try to fix it, the problem only grows deeper. This paradox is one of the oldest in philosophy, going back to ancient Greece. A thinker named Epimenities is often credited with it when he declared, "All Cretans are liars," while he himself was a Cretan. If what he said was true, then he was lying. But if he was lying, then what he said wasn't entirely true, and round it goes. The liar paradox shows us that language and logic can fold in on themselves in ways that make meaning collapse. On a deeper level, this paradox challenges us to think about truth itself. How do we define what's true and what's false when a statement can contain both at the same time? In everyday life, we like to believe that something is either right or wrong, but the liar paradox exposes the cracks in that black and white view. It forces us to question whether truth is always something clear and absolute, or whether sometimes it slips into gray areas where our logical systems fail. The liar paradox also plays a role in modern mathematics, computer science, and even artificial intelligence. Systems that rely on strict logical rules often stumble when they encounter self-referential statements. Imagine a computer program that is told, "This program will never stop running," If it tries to evaluate that statement, it can get stuck in an endless loop, unable to decide what's correct. That is the modern echo of the ancient paradox. What makes the liar paradox so powerful is its simplicity. With just a few words, it can break our understanding of logic wide open. It shows us that language is not just a tool, but also a trap, and sometimes the structure of what we say creates problems that no answer can solve. The ship of Thesus. Now, imagine an ancient wooden ship, the legendary ship of Theseus. Over time, as the years pass, the planks of the ship begin to rot. One by one, each plank is replaced with a brand new one, until finally, not a single piece of the original ship remains. And here's the question: is it still the same ship? At first, you might say yes. After all, it looks the same, it functions the same, and it has carried its identity forward through time. But then another puzzle makes it harder. Suppose someone had carefully collected all of the old planks as they were removed and rebuilt a ship using only those original pieces. Which one, then, is the real ship of Theseus? The one that has been gradually repaired, or the one made out of the original wood? This paradox digs deep into questions of identity and change. Are we defined by the material that makes us up, or by the continuity of our existence? The ship of Theseus is not just about boats, it's about us as human beings. Every cell in your body is replaced over time. You are physically not the same person you were years ago, yet you still feel like you are you. So, what truly makes you, you? Is it your body, your memories, your soul, or something else entirely? Philosophers, scientists, and even modern thinkers in technology have used this paradox to debate everything from the nature of personal identity to the possibility of mind uploading and artificial intelligence. If your mind could be transferred into a computer, would that digital version still be you, or just a copy? The ship of Theseus echoes in every one of those questions. Ultimately, this paradox teaches us that identity is more than just physical parts. It's about continuity, perception, and meaning. Whether it's a ship sailing through history or a person living through time, the ship of Theseus reminds us that identity is a puzzle without a perfect answer, but it is one worth thinking about. The Sorites heap paradox. Picture a pile of sand. If you take away one single grain of sand, it's still a heap. If you take away another grain, it's still a heap. But what happens if you keep removing grains, one by one? At what exact point does the heap stop being a heap? Can you ever identify the exact grain that transforms a heap into not a heap? This is the Sorites, or heap, paradox. It looks like a simple problem of language, but it reveals something much deeper about how we draw boundaries in a world that is often continuous. Our minds like clear categories, heap or not heap, tall or short, rich or poor. But reality doesn't always work in neat boxes. Instead, it slides gradually from one state to another, making it impossible to say with certainty when a change truly happens. The paradox applies not only to piles of sand, but to everyday life. When does someone go from being bald to not bald? When does a person stop being young and become old? When does a group of actions become a habit? Or when does a series of small lies turn into dishonesty? The Sorites paradox shows us that our language is not always precise enough to handle gradual change. In philosophy, this is tied to the problem of vagueness. Words like heap, tall, or rich don't have sharp boundaries, yet we use them every day as if they do. The paradox pushes us to see the hidden fuzziness in the concepts we take for granted. Even in law, politics, and science, this paradox matters. Laws often rely on clear definitions. But where do we draw the line? For example, how many hours of work make someone employed? How much income makes someone wealthy? These are not just abstract puzzles, they are real-world problems where a vague boundary can have huge consequences. The Sorites paradox doesn't give us an easy answer. Instead, it teaches us humility about the limits of our definitions. It reminds us that much of reality flows in gradual shades, not sharp edges, and that we should be careful when we act as if words can capture the complexity of the world. Zeno's Achilles and the Tortoise. Imagine a race between the legendary Greek hero Achilles, known for his incredible speed, and a slow-moving tortoise. To make it fair, the tortoise is given a head start. Now, Zeno asks us to think about what happens when Achilles starts running. By the time Achilles reaches the point where the tortoise began, the tortoise has already moved a little farther ahead. When Achilles reaches that new point, the tortoise has moved yet again, just a small distance more. No matter how fast Achilles runs, the tortoise will always be slightly ahead, because every time Achilles arrives at a spot, the tortoise has already inched forward. On the surface, this seems absurd. Of course, Achilles will overtake the tortoise in real life. But Zeno's paradox isn't about running. It's about how we think of space and time. The race can be broken down into an infinite number of smaller and smaller steps. And in theory, Achilles would have to complete an infinite number of steps just to catch the tortoise. How can you finish an infinite number of tasks in a finite amount of time? This paradox challenges our understanding of motion and infinity. It forces us to ask, is motion real, or is it just an illusion created by our senses? Ancient philosophers debated this deeply, and even today, mathematicians and physicists wrestle with the concept of infinity. The paradox reveals that dividing space and time into infinite parts can lead us to contradictions that don't match up with physical reality. Modern mathematics and calculus eventually offered a solution. By summing an infinite series of shrinking distances, we can show that Achilles does, in fact, catch the tortoise. But Zeno's paradox still carries a powerful lesson. It reminds us that the world doesn't always behave the way our logic expects. Sometimes, what seems obvious hides a much deeper mystery about how time, motion, and infinity truly work. Zeno's dichotomy paradox. Now, let's look at another of Zeno's famous puzzles, the dichotomy paradox. Imagine you are about to walk across a room. Before you can reach the other side, you first need to get halfway there. Once you're halfway, you must cover half of the remaining distance, then half of what's left after that, and then half again. The journey is broken into an endless sequence of halves. No matter how far you go, there's always another half to travel. By this reasoning, motion should be impossible, because you can never complete an infinite number of steps. Of course, we know we can cross a room. You walk, you take steps, and eventually you arrive. But the paradox isn't trying to deny everyday experience. It's showing how our understanding of infinity clashes with reality. If every action can be divided into smaller and smaller steps, and if those steps go on forever, then how do we ever finish anything? This paradox is about the tension between the infinite and the finite. It challenges us to think about whether infinity is just an abstract idea or something that truly exists in the fabric of reality. The dichotomy paradox points to the strange way that infinite processes seem to coexist with finite outcomes. You can, in fact, walk across the room, but only because infinite steps can be compressed into a finite span of time. Later, mathematics solved this puzzle using the concept of converging series. Even though there are infinitely many halves, the total distance adds up to something finite. But the paradox continues to haunt philosophy because it forces us to ask, what does it really mean to say something is infinite? Is infinity something real, or is it just a trick of language and logic? The dichotomy paradox teaches us that the everyday act of moving across a space hides one of the deepest mysteries of the universe. Zeno's arrow paradox. Finally, imagine an arrow flying through the air. At any single instant of time, if you freeze the arrow in your mind, it appears motionless, simply occupying one spot in space. If at every instant the arrow is at rest, then how can it ever be in motion? If every moment is just a frozen picture, then motion is nothing more than a collection of still frames, and movement itself becomes an illusion. This is Zeno's arrow paradox, and it cuts to the heart of how we understand time. Is time a continuous flow, or is it made up of countless frozen moments strung together, like frames in a film reel? If reality is just a sequence of still instants, then motion seems impossible. But if time is a flow, how do we explain it using the logic of moments? The paradox reveals the difficulty of defining motion without assuming time is something more than snapshots. It raises questions about whether the universe is truly continuous, like a smooth river, or discrete, like a collection of digital images. Even modern physics grapples with this. In quantum mechanics, time and motion may not behave the way we expect, and at the smallest scales, the universe could be more granular than continuous. The arrow paradox teaches us that what feels obvious, that things move, becomes deeply puzzling when you break it down logically. It shows that the way we divide time and space affects how we see reality itself. Philosophers and scientists still use this paradox as a reminder that motion, time, and existence are not as straightforward as they appear. Zeno's stadium paradox. Now, picture a stadium filled with 3 rows of objects, one row standing still, and 2 other rows moving in opposite directions past each other at equal speeds. At first glance, this seems simple enough. If one moving row passes the stationary objects in a certain amount of time, it should take the same time to pass the objects in the other moving row. But Zeno argued that if you break the motion down into moments, strange contradictions appear. For example, when one moving object passes another that's traveling in the opposite direction, it seems to happen in half the time it takes to pass a stationary one. This suggests that time itself can be both halved and doubled at the same moment, creating an inconsistency. The paradox is not really about objects in a stadium. It's about how dividing time and motion into discrete segments can create logical contradictions. The stadium paradox asks a deeper question. Is time something that flows continuously, or is it made up of indivisible units, like snapshots? If time is continuous, then how do we make sense of these strange inconsistencies? But if time is granular, with smallest units, then how does smooth motion even exist? Modern physics still wrestles with this problem. Some theories, especially in quantum mechanics, suggest that the universe may indeed have a minimum unit of time, called the Planck time, below which our concepts of before and after break down. The stadium paradox, though ancient, eerily anticipates these modern debates. It forces us to confront the possibility that our everyday understanding of motion and time might only be an illusion built on incomplete knowledge. Russell's paradox. At the start of the 20th century, the mathematician and philosopher Bertrand Russell discovered a paradox that shook the foundations of logic and mathematics. Imagine a library of sets, collections of things. Some sets can even contain other sets. Now consider the set of all sets that do not contain themselves. Does this set contain itself? If it does contain itself, then by definition, it should not. But if it does not contain itself, then by definition, it should. Just like the Barber paradox, this creates a contradiction that cannot be resolved. This is Russell's paradox. It may sound like wordplay, but its impact was massive. At the time, mathematics was being built on the idea that sets could be used to construct all numbers and logical truths. Russell's paradox revealed a fatal flaw in that foundation, that if you allow unrestricted self-reference, contradictions will emerge. It was like discovering cracks in the very bedrock of modern logic. This paradox forced mathematicians and philosophers to rethink their systems. It led to new developments like set theory with stricter rules, type theory, and ultimately reshaped the way logic and mathematics were understood in the 20th century. Beyond math, it teaches us a universal lesson. When rules or systems are allowed to refer to themselves without limits, contradictions are almost inevitable. Russell's paradox is more than just a puzzle. It is a warning that logic itself is not immune to collapse when we push it too far. It shows that even the most precise systems of human thought can fall apart if they are not carefully constructed. Buridan's bridge. This paradox comes from a story about the philosopher Jean Buridan. Imagine Socrates standing before a bridge guarded by Plato. Plato sets a condition. If Socrates tells the truth, he may cross. If he lies, he will be thrown into the water. Socrates then says, "You will throw me into the water." Now the dilemma begins. If Plato does throw Socrates into the water, then Socrates' statement was true, and he should have been allowed to cross. But if Plato allows him to cross, then the statement was false, and Socrates should have been thrown into the water. No matter what Plato does, he ends up breaking his own rule. Buridan's bridge is a paradox about prediction, truth, and authority. It shows how rigid rules can collapse when they are forced into self-referential situations. The guard's conditions seem logical at first, but Socrates cleverly crafts a statement that traps the rule in a contradiction. This paradox is not just a clever trick, it highlights the limitations of absolute rules in dealing with real-life complexity. In law, contracts, or even everyday promises, situations can arise where conditions contradict themselves, leaving no clear solution. Buridan's bridge reminds us that rules must sometimes bend or adapt to context, because rigid systems can be broken with nothing more than a carefully chosen sentence. Philosophically, it raises deep questions. Can truth always be applied mechanically, or does it require human judgment? Are rules truly absolute, Or are they always vulnerable to paradoxes when faced with clever manipulation? Buridan's bridge is not just a riddle between Socrates and Plato. It's a timeless lesson about the fragile balance between logic, language, and reality. The omnipotence paradox. The omnipotence paradox asks a question that sounds simple but carries enormous weight. Can an all-powerful being create a stone so heavy that even they cannot lift it? If the being can create such a stone, then there is something they cannot do: lift it. If they cannot create it, then there is something they cannot do: create the stone. Either way, the idea of unlimited power seems to collapse under its own weight. This paradox isn't really about stones or lifting. It's about whether the concept of absolute power is logically possible. If omnipotence means the power to do absolutely anything, then even contradictions must be possible. But contradictions, like a square circle or an unliftable stone, don't actually make sense in logic. So, does omnipotence include the power to do the logically impossible, or is it limited by reason itself? Philosophers and theologians have debated this paradox for centuries. Some argue that omnipotence doesn't mean doing the impossible, but doing everything that is logically possible. Others say that the very idea of absolute power is flawed, because power must always operate within some framework of rules. The omnipotence paradox shows us that language can create problems that may not exist in reality. By combining ideas like all-powerful with impossible tasks, we build contradictions that trap us in circular thinking. Still, the paradox is important because it forces us to confront the limits of concepts we often take for granted, like power, logic, and even the divine. At its core, this paradox teaches us that some questions cannot be answered, not because they're too deep, but because the way they're framed is broken. It challenges us to think more carefully about what power really means, and whether infinity can truly be captured in human language. The paradox of the unexpected hanging. Imagine a judge sentencing a prisoner to be hanged sometime in the coming week, but with a twist. The execution will happen on a weekday, and it will be a complete surprise. The prisoner will not know the day until the executioner comes for him. The prisoner begins to think. He reasons that it cannot be Friday, because if he survives until Thursday night, then he will know the execution must be on Friday, and that would ruin the surprise. So, he eliminates Friday. Then he thinks it cannot be Thursday, because by Wednesday night, he would know it must be Thursday. Step by step, he eliminates every day of the week, concluding that the hanging can never happen as a surprise. But when the executioner comes for him on Wednesday, he is completely shocked. The hanging is both a surprise and exactly as the judge promised. This paradox plays with logic, prediction, and self-reference. The prisoner's reasoning seems flawless, yet it collapses when reality plays out. The paradox lies in how knowledge of a future event can make that event impossible, and yet it can still happen in a way that surprises us. The unexpected hanging has fascinated philosophers, logicians, and mathematicians because it blurs the line between reasoning and reality. It shows how human attempts to predict the future can fall into traps when the rules themselves are designed to twist logic against us. The paradox highlights the tension between what we think we know and what actually unfolds in life. At a deeper level, it asks us whether true surprises can exist in a logical world. Can we ever really predict everything, or will life always find a way to outsmart us? The unexpected hanging reminds us that certainty can be an illusion, and that the future holds mysteries even when we believe we've reasoned them away. The lottery paradox. Now, imagine a lottery with millions of tickets. You know that only one ticket will win. For each individual ticket, you are almost certain it will lose. The odds are overwhelmingly against it. So, for each ticket, it seems rational to believe it will not win. But if you believe that about every single ticket, then you're also believing that no ticket will win, which you already know is false. This is the lottery paradox. It reveals a clash between probability, rational belief, and certainty. On the one hand, it is reasonable to assume that any single ticket will not win. On the other hand, it is unreasonable to believe that all tickets will lose because you know one must win. The paradox shows that individually rational beliefs can add up to something irrational when combined. This puzzle is not just about gambling. It connects to deeper questions about knowledge and probability in everyday life. We often make decisions based on what is likely, even though the unlikely can and does happen. The paradox forces us to ask, what does it mean to know something? Is it enough that it's almost certain, or does true knowledge require absolute certainty? Philosophers and logicians use the lottery paradox to study how probability interacts with belief. It has applications in law, science, and artificial intelligence, where decisions often have to be made based on uncertain information. The paradox reminds us that rational thinking must deal with uncertainty carefully because probability can mislead us into contradictions if we aren't cautious. At its heart, the lottery paradox teaches us about humility. Even when the odds point strongly in one direction, reality may surprise us. It warns us not to confuse probability with certainty, and it challenges us to think more deeply about what it means to believe something is true. The paradox of the ravens, Hemple's paradox. Imagine you want to test the statement, all ravens are black. At first, it seems easy. Every time you see a black raven, it supports the claim. But here comes the twist. Logically, the statement, all ravens are black, is equivalent to, everything that is not black is not a raven. That means if you see a green apple, it too confirms the statement, because the apple is not black, and it is not a raven. Now, this feels strange. How can looking at a piece of fruit tell us anything meaningful about the color of ravens? The paradox shows a conflict between logic and intuition. On one hand, the apple really does support the claim when framed logically. On the other hand, it feels absurd to say that apples provide evidence about ravens. The paradox of the ravens raises a big question. What actually counts as evidence? In science and everyday reasoning, we think of evidence as something that directly connects to the subject we're studying. But the paradox shows that logic sometimes stretches the definition of evidence so far that it no longer makes sense intuitively. This paradox has been widely debated in philosophy of science. It highlights the tension between formal logic and human understanding. Do we trust the strict logic that says apples confirm the rule, or do we trust our intuition that real evidence should be directly related? At a deeper level, the paradox of the ravens reminds us that evidence is not just about logic. It's also about context, relevance, and meaning. Not every logical confirmation feels like real confirmation. The paradox forces us to think more carefully about how we gather knowledge and what truly strengthens our beliefs. The two envelopes paradox. Imagine you are given two envelopes, and you're told that one contains twice the amount of money as the other. You don't know which is which. You pick one envelope, but before opening it, you're offered a chance to switch. At first, it seems like it doesn't matter. The envelopes look identical, but then you start reasoning. Suppose the envelope you picked has X dollars. Then the other envelope must contain either 2x or x2. If you switch, you have a 50% chance of doubling your money and a 50% chance of losing half. The math looks tempting because the expected value of switching always seems higher than staying. But here's the problem. That reasoning works no matter which envelope you choose. By that logic, you should always switch. And yet, if you switched back and forth forever, nothing would change. This is the two envelopes paradox. It shows how probability and expectation can trick us into endless loops of indecision. On the surface, the reasoning feels airtight, but it hides a flaw in how we calculate the probabilities and expectations. The paradox is more than a gambling puzzle. It connects to decision theory, economics, and philosophy. It forces us to ask, how do we make rational choices when the information is incomplete, or when reasoning loops back on itself? The two envelopes paradox shows that sometimes rational thinking leads to contradictions, and that decisions require more than just abstract logic. At its core, this paradox teaches us that not all problems have neat solutions. It reminds us that when we're faced with uncertainty, our reasoning can be misled by assumptions that seem correct, but don't hold up under scrutiny. The Monty Hall problem. Now, imagine you're on a game show. You're shown 3 doors. Behind one door is a car, and behind the other 2 are goats. You pick a door, hoping it's the car. Before opening it, the host, Monty Hall, opens one of the other doors to reveal a goat. Then he gives you a choice. Do you want to stick with your original door or switch to the other unopened one? Most people think it doesn't matter. There are 2 doors left, so it must be a 50-50 chance. But the math tells a different story. If you stay with your original choice, your chance of winning the car is only 1 in 3. If you switch, your chance doubles to 2 in 3. This result feels completely counterintuitive. How can switching improve your odds when only 2 doors are left? The answer lies in the way the problem is structured. At the start, you had only a 1 in 3 chance of picking the car. The host's action of revealing a goat doesn't change your initial odds. It just shifts the probability toward the other unopened door. Switching is the smarter move, even if it feels unnatural. The Monty Hall problem is more than a game show trick. It reveals how human intuition often struggles with probability and uncertainty. Our minds are not naturally wired to think in terms of statistics, and we are easily misled by what feels fair or even. Philosophers and psychologists love this paradox because it shows how our reasoning can fail in the face of uncertainty. It also applies to real life, in decisions about risk, strategy, and chance. Our gut instincts are not always reliable. The Monty Hall problem teaches us that sometimes the counterintuitive choice is the right one, and that logic, not intuition, must guide us when probability is involved. Simpsons paradox. Imagine you're looking at statistics that seem to show one clear trend, but when you break them down into smaller groups, the trend completely reverses. That's the strange and fascinating world of Simpsons paradox. For example, suppose a new drug appears to help patients when you look at the overall data. But when you separate the patients into groups, men and women, or young and old, suddenly you see that the drug actually harms every single group. How can it help everyone overall, but hurt everyone individually? This paradox happens because averages can hide deeper patterns. When you combine groups, the numbers can shift in ways that give a false impression. It shows us that statistics, while powerful, can also mislead us if we don't pay attention to the context. The lesson of Simpsons' paradox is huge. It teaches us that data never speaks for itself. It must be interpreted carefully. Politicians, advertisers, and even scientists can fall into the trap of drawing wrong conclusions from data if they ignore hidden variables. The paradox reminds us that numbers can be true in one sense and false in another, depending on how they're grouped. In everyday life, this paradox warns us not to accept surface-level statistics at face value. It urges us to dig deeper, to ask what's behind the numbers, and to remember that truth can sometimes be buried under misleading patterns. Simpsons' paradox is not just a statistical trick. It's a reminder of how easily our understanding of reality can be shaped by the way we choose to look at it. The boy or girl paradox. Imagine a family has 2 children. You meet one of them and find out that it's a boy. Now here comes the puzzle. What are the chances that the other child is also a boy? At first, most people think it's 50-50. Either it's a boy or a girl, but the real math tells a different story. If you lay out all the possibilities, you have boy-boy, boy-girl, girl-boy, and girl-girl. But since you already know that at least one child is a boy, you eliminate the girl-girl option. That leaves 3 possibilities: boy-boy, boy-girl, and girl-boy. Out of those 3, only one is boy-boy. That means the actual chance of both children being boys is not 50% but 1 in 3. This paradox shows how tricky probability can be when we don't carefully define the conditions. The confusion comes from the difference between at least one boy and the first child is a boy. Depending on the wording, the odds shift. The boy or girl paradox teaches us an important lesson. Probability is not just about numbers, but about how questions are framed. A small change in perspective can completely change the answer. It also reminds us that our intuition often struggles with chance. We jump to conclusions that feel right, but don't hold up under careful reasoning. In a world full of uncertainty, this paradox highlights the need for clear thinking. Whether it's about family puzzles, risks, or real-world decisions, the boy or girl paradox shows how easily our minds can be fooled by the way information is presented. The Sleeping Beauty paradox. Now, picture this thought experiment. Sleeping Beauty agrees to take part in an experiment. On Sunday night, she's put to sleep. A fair coin is tossed. If it lands heads, she will be woken up on Monday, interviewed, and then put back to sleep with her memory erased. If it lands tails, she will be woken up on both Monday and Tuesday, interviewed each time, with her memory erased after each day. When Sleeping Beauty wakes up, she has no idea which day it is. The question is, what should her belief be about the coin toss? Should she believe it's a 50-50 chance, since that's the original probability? Or should she think it's more likely tails, because in that case she is woken up twice, giving her more chances to experience the awakening? This paradox has divided philosophers and mathematicians. Some argue she should stick with 50-50, since the coin itself is fair. Others say she should reason it's 2 out of 3 in favor of tails, since 2 possible awakenings happen in that scenario. Both sides have strong arguments, and no clear consensus exists. The Sleeping Beauty paradox isn't just a riddle. It's a deep challenge to our understanding of probability and self-locating belief. It forces us to ask, what does it mean to assign probabilities when our own perspective is part of the uncertainty? This paradox matters beyond philosophy. It touches on decision theory, the way we think about time, and even interpretations of quantum mechanics, where multiple possibilities can exist at once. It reminds us that probability is not always straightforward, especially when our own position in the problem changes the outcome. In the end, the Sleeping Beauty paradox is a haunting reminder that even the simplest scenarios, a coin toss, a night's sleep, can unravel into mysteries that challenge our very sense of reality. The paradox of the court. The paradox of the court, also known as the case of Protagoras and Euthyphus, is a story about a law teacher and his student. Protagoras, a skilled lawyer, agreed to teach Euthyphus on one condition. Euthyphus would pay his fee only after he won his first court case. But after finishing his training, Euthyphus avoided going to court at all. Tired of waiting, Protagoras decided to sue him, reasoning that no matter what happened, he would get his money. If Protagoras won the case, the court would order Euthyphus to pay him. If Euthyphus won, then by definition he had won his first case, and the contract required him to pay his teacher. Either way, Protagoras believed he couldn't lose. But Euthyphus was just as clever. He argued the opposite. If he won the case, then the court would rule he owed nothing, and that would override the contract. If he lost, then he still wouldn't have won his first case, which meant he didn't yet owe Protagoras anything. In his reasoning, no matter the outcome, he didn't have to pay. This paradox is more than just a courtroom trick. It's about the clash between contracts, logic, and interpretation. Both sides appear to be correct, yet they cancel each other out, leaving no clear resolution. It highlights how rules, when framed cleverly, can twist into contradictions. The paradox of the court is a lesson about the limits of rigid logic in human affairs. Laws, contracts, and agreements depend not only on rules, but also on context and interpretation. It shows us that, in the real world, reasoning can be so tightly wound that it becomes impossible to untangle without judgment. And it reminds us that clever arguments, no matter how logical they sound, don't always lead to justice. The bootstrap paradox. Now, step into the world of time travel. Imagine someone travels back in time and gives Shakespeare a copy of Hamlet. Shakespeare copies it word for word and publishes it as his own. Centuries later, someone takes that same book and travels back to give it to Shakespeare again. Where did Hamlet actually come from? Who wrote it? This is the bootstrap paradox, also called a causal loop. It happens when an object or piece of information is sent back in time and becomes the very cause of itself. The paradox is that it seems to exist without ever having an origin. The book was never created in the first place. It simply exists in a loop, passed endlessly from future to past. The bootstrap paradox raises deep questions about causality, creation, and the flow of time. It suggests that time travel might create loops where cause and effect lose their meaning. If something can exist without an origin, what does that say about free will and creativity? Are we the authors of our own actions, or are we trapped in loops that go on forever? This paradox fascinates scientists and science fiction writers alike. It shows up in countless stories about time travel, where characters struggle with objects or knowledge that seem to appear out of nowhere. It challenges the very foundations of cause and effect thinking, suggesting that our universe might hold stranger possibilities than we can imagine. At its heart, the bootstrap paradox is not just about time machines. It's about the mystery of origins, where things come from, and whether everything must have a beginning. It reminds us that time, one of the things we take most for granted, may hold secrets that stretch beyond human understanding. The grandfather paradox. The grandfather paradox is one of the most famous and unsettling puzzles of time travel. Imagine traveling back into the past and accidentally, or deliberately, preventing your own grandfather from meeting your grandmother. If they never meet, they never have children, and eventually you are never born. But if you were never born, then how could you have traveled back in time to stop them in the first place? This paradox creates a direct contradiction in cause and effect. If you change the past in a way that erases your own existence, then you can't have been there to make the change at all. But if you weren't there, then the past remains unchanged, and you were born, which means you could go back and change it. The cycle spins endlessly with no logical way out. The grandfather paradox goes far beyond family drama. It highlights the potential impossibility of changing the past. Some philosophers and physicists argue that time must be self-consistent, that no matter what you do in the past, events will always conspire to keep history intact. Others suggest that changing the past might create alternate timelines or parallel universes, where your actions branch reality into different paths. This paradox challenges our very ideas of freedom and destiny. If time travel is ever possible, do we have the power to alter the past, or are we locked into a timeline that resists change? The grandfather paradox forces us to confront the limits of human control, showing us that even with incredible technology, the laws of logic and causality might tie our hands. In the end, the grandfather paradox isn't just about time travel. It's about the relationship between past, present, and future. It makes us question whether our lives are fixed in a chain of causes, or whether we could ever truly break free. It remains one of the most haunting thought experiments in philosophy and science. The predestination paradox. The predestination paradox is one of the strangest puzzles in time travel. Imagine a traveler goes back in time to prevent an event from happening, but in the process of interfering, they accidentally cause that very event to occur. The attempt to change the past becomes the reason the past happened in the first place. For example, suppose someone travels back in time to stop a great fire from destroying a city. In trying to prevent it, they knock over a lantern, and that lantern ends up starting the very fire they were trying to avoid. This paradox reveals a haunting idea. What if time is a closed loop, and all attempts to change history are already part of history itself? In that case, free will becomes an illusion, because whatever you do in the past only fulfills what has already been written. The paradox suggests that events are locked into place, and any attempt to escape destiny may only tighten its grip. The predestination paradox raises profound questions about fate, causality, and freedom. Do we control our choices, or are we characters in a story already written? If every attempt to alter the past is doomed to preserve it, then maybe time itself is unchangeable. This idea shows up often in science fiction, where heroes try desperately to rewrite history, only to realize they are the very cause of the events they wish to stop. At a deeper level, this paradox touches on real human life. How often do we struggle against something, only to realize our very struggle creates the outcome we feared? The predestination paradox is not just about time machines. It's a mirror of our battles with destiny and the patterns we cannot seem to escape. The Fermi paradox. The Fermi paradox asks one of the biggest questions of all. If the universe is so vast, with billions of stars and countless planets that could support life, then where is everybody? Why, in a galaxy that should be teeming with civilizations, do we find silence? The paradox begins with the math. Even if only a tiny fraction of stars have planets with life, the numbers suggest that intelligent civilizations should be common. Some should have advanced far beyond us, perhaps capable of traveling between stars. If that's the case, then why haven't we seen any evidence? No signals, no spacecraft, no clear signs that we are not alone. There are many possible answers, but none are fully satisfying. Maybe intelligent life is far rarer than we think. Maybe civilizations destroy themselves before they reach the stars. Maybe they are out there, but choose to remain hidden. Or maybe they exist on levels of reality we can't even perceive, like ants trying to understand a superhighway. The Fermi paradox is more than just science fiction. It challenges us to think about humanity's place in the cosmos. Are we truly alone, or are we just too early or too primitive to notice the others? It forces us to face uncomfortable possibilities. Perhaps intelligent life burns out quickly, or perhaps we are so small and insignificant that the universe simply doesn't notice us. What makes the Fermi paradox so powerful is its mix of hope and fear. On one hand, it inspires us to search, to listen, and to dream of connection. On the other, it whispers that maybe silence is the answer, and that the universe, in all its vastness, may be empty. Olbers' paradox. Olbers' paradox begins with a simple observation. If the universe is infinite and filled with stars, then the night sky should be blazing bright. Every line of sight should eventually land on a star, and the whole sky should glow like the surface of the sun. Yet when we look up at night, we see darkness sprinkled with points of light. Why? For centuries, this question puzzled astronomers. If the universe had existed forever and stars were everywhere, then the night should never be dark. The paradox suggested that something about our assumptions was wrong. Modern science eventually solved it. The universe is not infinite in age. It had a beginning with the Big Bang. Stars have not existed forever. They were born at certain times, and they die. The light from many distant stars has not had enough time to reach us yet, and as the universe expands, light stretches into longer wavelengths, dimming what we see. Olbers' paradox, though solved scientifically, remains a beautiful reminder of how a simple question can lead to profound discoveries. It shows how looking at the sky with childlike wonder can spark insights into the deepest truths of reality. The dark night is not an absence of light. It is a sign of the universe's history, its expansion, and its mystery. At a deeper level, Olbers' paradox teaches us that appearances can be deceiving. What looks like emptiness is actually full of hidden meaning. The quiet darkness of the night sky is not a failure of light, but the key to understanding the origin and structure of the cosmos. The twin paradox. The twin paradox comes from Einstein's theory of relativity, and it sounds like something out of science fiction. Imagine two identical twins. One stays on Earth, while the other travels into space at near the speed of light. After the space journey, the traveling twin returns home. According to relativity, the twin who went to space will have aged less than the one who stayed on Earth. But here's the puzzle. From the traveler's perspective, wasn't the Earth twin the one who was moving? Shouldn't the roles be reversed? The paradox arises from the strange way time works in relativity. Time is not absolute. When you move very fast, close to the speed of light, time slows down for you compared to someone who is standing still. This effect is called time dilation, and it has been proven in real experiments with fast-moving particles and precise atomic clocks. The resolution comes from the fact that the traveling twin changes direction, accelerating and decelerating during the trip, while the Earth twin remains in one frame of reference. That break in symmetry explains why the traveling twin ages less. Still, the paradox challenges our intuition because we are so used to thinking of time as universal, the same for everyone. The twin paradox is more than just a physics riddle. It shows us that time is not the steady river we think it is. Time bends, stretches, and twists depending on motion and gravity. It forces us to confront the reality that time itself is relative, and that our everyday understanding of it is only a shadow of the truth. The black hole information paradox. Black holes are some of the strangest objects in the universe. They are formed when massive stars collapse under their own gravity, creating a region so dense that nothing, not even light, can escape. According to physics, anything that falls into a black hole should be gone forever. But here comes the paradox. What about information? In physics, there is a rule that information can never be truly destroyed. It may change form, but it cannot vanish. Yet black holes seem to break that rule. When matter falls in, it disappears behind the event horizon. If the black hole eventually evaporates through Hawking radiation, as Stephen Hawking predicted, then all the information about what fell in appears to be lost forever. That would mean a fundamental law of the universe has been broken. This is the black hole information paradox, one of the biggest unsolved problems in modern physics. Does information somehow escape in the radiation? Is it stored on the surface of the black hole, like a cosmic hologram? Or do we need a completely new theory of space, time, and quantum mechanics to explain it? The paradox forces us to confront the limits of our knowledge. It lies at the intersection of relativity, quantum mechanics, and cosmology, the three great pillars of physics that don't yet fit neatly together. At its heart, this paradox asks, does the universe keep perfect track of everything, or can information be lost forever? The answer will reshape our understanding of not just black holes, but reality itself. The paradox of tolerance. The paradox of tolerance comes not from physics, but from social philosophy. The thinker Karl Popper described it like this. If a society is completely tolerant, if it tolerates everything, including intolerance, then eventually the intolerant will destroy tolerance itself. In other words, unlimited tolerance leads to the death of tolerance. This paradox forces us to face a moral dilemma. On the one hand, tolerance is a virtue. the willingness to let others live, speak, and believe as they choose. But on the other hand, if we tolerate those who spread hatred, violence, or oppression, they may rise in power and crush the very freedom that allowed them to exist. So, the paradox suggests that to preserve tolerance, we must be prepared to refuse tolerance to the intolerant. This idea has real-world consequences. It applies to politics, free speech, and social harmony. Where do we draw the line between freedom of expression and protecting society from harm? If we allow dangerous ideologies to spread unchecked, do we risk losing everything we value? The paradox of tolerance is not just an abstract thought experiment. It's a warning. It teaches us that tolerance cannot be blind or passive. It must be active, thoughtful, and willing to defend itself. It asks us to confront the uncomfortable truth that freedom sometimes requires boundaries. At its core, this paradox is about balance. It reminds us that values like freedom, respect, and tolerance are not guaranteed. They must be protected, even if that means limiting those who would use freedom to destroy it. The prisoner's dilemma: imagine two criminals are arrested and placed in separate cells. They cannot communicate. The police offer each of them a deal. If one confesses while the other stays silent, the confessor goes free and the silent one gets a heavy sentence. If both confess, they both get a moderate sentence. If both remain silent, they both get only a light punishment. The rational choice seems simple: cooperate by staying silent. But here's the catch. Each prisoner knows the other might betray him, and if he doesn't confess, he risks getting the worst outcome. So, the logical strategy, from a purely self-interested point of view, is for both to confess, even though this leaves them both worse off than if they had stayed silent. This is the prisoner's dilemma, a paradox of cooperation and self-interest. It reveals a deep truth about human behavior. What seems rational for the individual can be irrational for the group. It plays out not just in prisons, but in politics, economics, business, and everyday life. From countries deciding whether to build weapons, to companies setting prices, to friends keeping or breaking trust, the dilemma is everywhere. The paradox teaches us that rationality is not always simple. Sometimes the best outcome requires trust, cooperation, and even risk, things that logic alone cannot guarantee. It challenges us to ask, do we protect ourselves at the expense of others, or do we trust others in the hope of creating something better together? The prisoner's dilemma shows us the fragile balance between fear and trust. It's a reminder that sometimes the smartest move isn't about winning alone, but about learning how not to lose together. Newcomb's paradox. Now imagine a strange game. A player faces two boxes, one transparent box that clearly contains 1,000, and one opaque box that may contain either 1 million or nothing. The player is told a powerful predictor, almost always right, has already decided what's in the opaque box. If the predictor believed the player would take both boxes, then the opaque box is empty. If the predictor believed the player would take only the opaque box, then it contains 1 million. Here's the paradox. Should the player take both boxes or just the opaque one? Logic pulls in two directions. One line of reasoning says, the predictor has already made its choice, so nothing you do now can change what's inside. You might as well take both boxes. But another line of reasoning says, because the predictor is nearly perfect, if you take both, it probably predicted that and left the opaque box empty. If you take only the opaque box, it likely predicted that too, and filled it with 1 million. Newcomb's paradox highlights a conflict between free will, prediction, and rational choice. Do we act as if the future is fixed, or as if our decisions still shape it? The paradox challenges the idea of independence in decision-making, because the predictor's accuracy ties your choice to the outcome in a way that defies simple logic. This puzzle has fascinated philosophers, mathematicians, and economists. It asks whether we should trust logic that looks at the present alone, or logic that takes into account patterns of prediction and expectation. At its core, Newcomb's paradox asks a haunting question. Do we truly control our choices, or are they already entangled with outcomes we cannot escape? The unexpected exam paradox. A teacher announces to her class, next week you will have a surprise exam. You won't know the day until it happens. The students begin to reason. They decide it cannot be on Friday because if they reach Thursday evening without a test, they will know it must be Friday, and that would ruin the surprise. So they eliminate Friday. But then, by the same logic, Thursday is impossible too, because by Wednesday evening, they would know it must be Thursday. Step by step, they eliminate every day of the week, convincing themselves that the surprise exam cannot happen at all. But when the teacher gives the exam on, say, Wednesday, the students are shocked, proving the teacher right. The exam was unexpected after all. The unexpected exam paradox is very similar to the unexpected hanging paradox, but it applies to knowledge, reasoning, and surprise in a broader context. It shows how logic can collapse when applied to self-referential situations. The students' reasoning seems flawless, yet it blinds them to the very surprise they were promised. This paradox forces us to think about the limits of prediction and the nature of knowledge. Can we ever be certain about the future? Or does the act of predicting it sometimes change the outcome? It also highlights the tension between logic and reality. Reasoning can lead us into conclusions that life itself overturns in an instant. The unexpected exam paradox is a reminder that not everything can be perfectly reasoned out. Some truths only reveal themselves when they happen, and sometimes the very structure of a problem ensures that surprise will always win. The teletransportation paradox: imagine a futuristic machine that can teleport you anywhere instantly. The way it works is this. It scans your entire body at the atomic level, destroys your original body, and then reconstructs a perfect copy of you somewhere else using new matter. The copy looks like you, thinks like you, remembers everything you do. But here's the haunting question: is that still you? From the outside, it seems like you simply stepped into the machine and arrived somewhere else. But from the inside, the paradox becomes disturbing. If the original you is destroyed and only a copy appears, then what happened to your consciousness? Did you die in the machine while someone else, who only thinks they are you, walks away on the other side? The teletransportation paradox asks whether identity is tied to physical continuity or psychological continuity. Are you the same person if your body is replaced by a copy that behaves exactly the same? If memory and personality are preserved, maybe yes, but if your actual consciousness ended the moment the machine destroyed you, then maybe no. This paradox isn't just science fiction. It forces us to ask what makes us who we are. Is it our bodies, our memories, or something deeper that cannot be copied? It connects to real debates in philosophy, neuroscience, and artificial intelligence. If one day we could upload minds into computers, would the digital version truly be us, or just a copy that believes it is? The teletransportation paradox is unsettling because it touches our deepest fear, the fear of losing ourselves. It reminds us that identity is fragile and mysterious, and that technology may one day push us to face questions that don't have easy answers. Moore's paradox comes from a simple but strange statement. It's raining, but I don't believe that it's raining. At first, it seems like nonsense. How can you say something is true while also claiming you don't believe it? Yet logically, the statement could describe a possible situation. It could be raining outside while you, for some reason, don't believe it. There's no contradiction in the facts themselves. The paradox lies in the act of saying it. If you truly believe it's raining, you can't also honestly say you don't believe it. The statement feels impossible, not because it can't be true, but because it cannot be sincerely asserted without self-contradiction. Moore's paradox digs deep into the relationship between truth and belief. It reminds us that knowing something and believing it are not always the same. Humans can hold conflicting states of mind, doubt, denial, or self-deception, even in the face of obvious truths. This paradox has influenced philosophy of mind and language, showing how communication depends not only on facts, but also on the alignment between belief and expression. It highlights the complexity of self-awareness, how we can know things on one level while refusing to accept them on another. In everyday life, Moore's paradox reflects our own contradictions. How often do we know something is true but act as if we don't? How often do people deny what is obvious to everyone else? The paradox forces us to confront the gap between truth, belief, and honesty, a gap that makes us uniquely human. The paradox of the stone. The paradox of the stone is a version of the omnipotence paradox, and it asks, can an all-powerful being create a stone so heavy that even they cannot lift it? If the answer is yes, then there is something the being cannot do. Lift the stone. If the answer is no, then there is something they cannot do. Create the stone. Either way, the idea of unlimited power seems to defeat itself. This paradox explores the limits of omnipotence. Can absolute power exist, or is it always bound by the laws of logic? Some argue that omnipotence does not include doing the impossible, like making a square circle or creating an unliftable stone. Others suggest that true omnipotence must go beyond human logic, meaning the question itself may not make sense. The paradox of the stone is not just about theology. It reflects a deeper problem with language and logic. Sometimes, the words we use can combine into statements that sound meaningful, but are actually contradictions. Asking if an all-powerful being can make an unliftable stone is like asking if they can make a four-sided triangle. The paradox forces us to see that not every question has an answer, because some questions are broken from the start. On a deeper level, it challenges our understanding of power and limits. It shows that infinity is not something the human mind can fully grasp, and that even our attempts to define ultimate strength collapse into contradictions. In the end, the paradox of the stone isn't about rocks at all. It's about the boundaries of logic, the mystery of power, and the way language can trap us in puzzles that can never be solved. Quin's paradox isn't as famous as some others, but it plays with the same idea of self-reference and contradiction. It asks us to imagine a situation where a statement denies itself in such a way that it can never be resolved. Think of it like this. The next sentence is true, the previous sentence is false. The moment you try to evaluate it, you end up stuck. If the first sentence is true, then the second sentence must also be true. But if the second is true, then the first is false. Round and round it goes, with no way to settle the puzzle. The essence of Quin's paradox is that it reveals the danger of circular reasoning. Language can fold back on itself and create endless loops where truth and falsehood lose all meaning. This isn't just a clever word trick. It's a serious problem for logic and mathematics, where self-reference can collapse entire systems. This paradox shows us that logic, as powerful as it is, can be broken by its own structure. It teaches us that rules can't always apply to themselves without creating contradictions. In a way, it's a cousin to Russell's paradox and the liar paradox, exposing the cracks in systems we thought were solid. At a deeper level, Quin's paradox reminds us of the human mind itself. We often get caught in thought loops, second-guessing and contradicting ourselves in ways that trap us. Just like logic, we are vulnerable to spirals of self-reference. The paradox is a mirror for the way thinking itself can become its own worst enemy. Carrol's tortoise paradox, Lewis Carrol, the author of Alice in Wonderland, was also a mathematician and logician. He created a puzzle known as the tortoise paradox, where he showed how logic can never fully prove itself. Imagine Achilles arguing with a tortoise. The tortoise accepts a logical rule. Say, if A and B are true, then C must be true. Achilles gives the tortoise A and B, but the tortoise refuses to accept C, unless Achilles gives him another rule. If A and B, then C. Achilles agrees and gives it, but the tortoise still refuses unless Achilles gives yet another rule to connect the first ones. No matter how many rules Achilles adds, the tortoise can always demand more, making the chain endless. The paradox reveals a deep problem. Logic itself can't force someone to accept its conclusions. You can keep stacking rules forever, but at some point, you have to accept the system without further justification. This is not just a story about Achilles and a tortoise. It's about the foundations of reasoning itself. How do we know logic works? At some level, we just have to take it on trust, or else we end up in an infinite regress where proofs never end. Carrol's tortoise paradox is funny and playful, but it carries a serious lesson. It shows that reasoning has limits, and that every system rests on some assumptions that can't be proven from within. It's a reminder that even logic, the tool we use to build knowledge, is not as airtight as it appears. The paradox of inquiry. Meno's paradox. This paradox comes from Plato's dialogue, Meno, and it asks a haunting question. How can you search for something if you don't know what it is? If you already know it, then there's no need to search. But if you don't know it, then how would you even recognize it when you find it? Either way, inquiry seems impossible. This is Meno's paradox, and it cuts to the core of learning, discovery, and knowledge. On the surface, it looks like a simple trap in reasoning, but it points to something profound. The mystery of how humans move from ignorance to understanding. Plato's answer was the theory of recollection. the idea that knowledge is already within us and learning is simply remembering what our soul already knows. But even without accepting that, the paradox forces us to reflect on how we recognize truth when we stumble upon it. In modern terms, the paradox applies to science, art, and even personal growth. How do we make discoveries about the unknown when we don't yet know what we're looking for? How do breakthroughs happen if, logically, we shouldn't be able to find what we can't define? The paradox of inquiry reminds us that human curiosity defies simple logic. Our minds are built to search, even without knowing exactly what we're searching for. It teaches us that discovery is not a straight line, but a leap into the dark, guided by intuition, imagination, and the strange ability to recognize meaning when it appears before us. The paradox of analysis. The paradox of analysis comes from the philosopher C.H. Langford and later discussions by G.E. Moore. It begins with a simple question. How can an analysis of a concept be both correct and informative at the same time? If an analysis is correct, it should mean exactly the same thing as the concept it explains. But if it means exactly the same thing, then it doesn't really tell us anything new. On the other hand, if the analysis does add something new, then it can't mean exactly the same thing, and therefore, it isn't perfectly correct. This paradox strikes at the heart of philosophy and language. When we define or analyze an idea, like, knowledge is justified true belief, are we truly explaining it, or just repeating it in slightly different words? If definitions and explanations only restate what we already know, then how do we ever expand understanding? The paradox of analysis shows that explanation is more mysterious than it seems. Often, what feels like a fresh insight is really a way of shining light on something we already grasp intuitively. Analysis gives us clarity, not new truth, and that clarity itself becomes valuable. It's like looking at a familiar picture, but suddenly seeing the details you never noticed before. At a deeper level, the paradox is a reminder that knowledge isn't just about information, it's about perspective. Even if an analysis does not add new facts, it reshapes how we understand the old ones. The paradox of analysis teaches us that progress in thought sometimes comes not from discovering brand new truths, but from sharpening and reframing the truths we already hold. The Gettier problem. For centuries, philosophers believed they had nailed down the definition of knowledge. It is justified true belief. To know something means you believe it. Your belief is justified by good reasons, and it happens to be true. But in 1963, Edmund Gettier published a short paper that shook philosophy to its core. He showed that even if all three conditions are met, there can still be cases where we wouldn't say someone truly knows something. Here's an example. Imagine you see a clock on the wall that reads 2 o'clock. You believe it's 2 o'clock, and you're justified because the clock normally works. By chance, it really is 2 o'clock, but the clock stopped 12 hours ago. Do you truly know the time? According to the definition, you have a justified true belief. Yet intuitively, it feels wrong to say you actually know, because your justification was flawed. These kinds of scenarios, called Gettier cases, reveal that knowledge is trickier than philosophers once thought. They show that being right for the wrong reasons doesn't count as real knowledge, even if your belief turns out true. The Gettier problem launched decades of debate and countless attempts to refine the definition of knowledge. It raised questions about luck, justification, and the difference between guessing correctly and truly knowing. At its heart, the Gettier problem reminds us that knowledge is fragile. It shows how thin the line can be between confidence and truth, and how easily our beliefs can rest on shaky ground. It forces us to ask, when we say we know something, are we standing on solid foundations, or are we just lucky enough to be right? The Epimenities paradox. The Epimenities paradox is one of the earliest recorded paradoxes, and it still fascinates thinkers today. Epimenities, a philosopher from Crete, is said to have declared, "All Cretans are liars." The problem is obvious. If he is telling the truth, then he himself, being a Cretan, must be lying. But if he isn't, then not all Cretans are liars, which means his statement might actually be true. Either way, the logic twists back on itself. This is a version of the liar paradox, but it highlights the problem of self-reference in a particularly sharp way. When a statement refers to the truth or falsehood of a group that includes the speaker, contradictions arise. The Epimenities paradox shows how fragile language can be. Words can create loops where meaning collapses, and truth becomes impossible to pin down. It's a reminder that even the simplest sentences can carry traps when they refer back to themselves. On a deeper level, this paradox reflects something human. We often make sweeping generalizations about people, places, or life itself, only to realize that we ourselves are part of what we're criticizing. Just like Epimenities, we can't escape the loops our own words create. Philosophically, the paradox has shaped debates about logic, truth, and even theology. It shows that self-reference is a powerful but dangerous tool, and it reminds us that sometimes the very act of speaking can pull us into contradictions we cannot escape. The crocodile paradox. The crocodile paradox is one of those puzzles that sounds almost like a riddle from a fairy tale, yet it hides deep philosophical problems. Imagine a crocodile that steals a child. The crocodile promises the parent that the child will be returned if, and only if, the parent can correctly predict what the crocodile will do next. If the parent says, "You will not return my child," the paradox is said. If the crocodile planned to return the child, then the parent's statement would be false, so the crocodile shouldn't return the child. But if the crocodile planned not to return the child, then the parent's prediction would be true, which means the crocodile is obliged to return the child. Either way, the crocodile's promise creates a contradiction it cannot logically resolve. This paradox explores the limits of prediction, truth, and conditional promises. It shows how rules that seem clear can break when they are tied to self-referential situations. The crocodile's promise collapses because it allows the outcome to be defined by the prediction itself, creating a logical loop. On a deeper level, the crocodile paradox mirrors real life. It represents the way promises and conditions can be manipulated into impossible situations. In law, contracts, or negotiations, sometimes the very terms of an agreement make it impossible to fulfill. The paradox reminds us that language can tie us in knots when it tries to bind the future with absolute certainty. It's not just a riddle about a crocodile, it's a warning about the fragility of words, promises, and logic when they start chasing their own tails. The donkey paradox, Buridan's ass. The donkey paradox, also known as Buridan's ass, is a thought experiment about choice, reason, and paralysis. Imagine a donkey placed exactly halfway between two identical piles of hay. The donkey is hungry and wants to eat, but both piles are the same size, the same distance away, and equally appealing. There is no rational reason to choose one over the other. So, what happens? Logically, the donkey should pick either pile, it doesn't matter which. But because the options are perfectly balanced, the donkey has no reason to favor one side. In the story, the donkey ends up starving to death, trapped in indecision despite having food right in front of it. This paradox shows the limits of pure rationality. If reason alone guided decisions, then in cases of perfect equality, choice would become impossible. It highlights the importance of randomness, impulse, or even emotion in breaking ties and allowing action to happen. On a deeper level, the donkey paradox reflects human life. How often do we find ourselves stuck between two choices that seem equally good or equally bad, and waste precious time unable to decide? The paradox teaches us that waiting for perfect certainty can be fatal. Sometimes action itself is more important than the reasoning behind it. Philosophically, it raises the question of free will. If we act purely on reason, are we bound to freeze in situations of perfect balance? Or do we need something beyond reason, instinct, will, or creativity, to break the tie? The donkey paradox reminds us that life rarely gives us perfect certainty, and that sometimes survival depends on simply choosing. The paradox of value, diamond water paradox. The paradox of value, often attributed to Adam Smith, asks a simple but profound question. Why are diamonds, which are unnecessary for survival, so expensive, while water, which is essential to life, is so cheap? At first glance, this seems irrational. Water keeps us alive. Diamonds do nothing to sustain us. Shouldn't water be infinitely more valuable than diamonds? Yet in markets and human behavior, the opposite is true. This paradox challenges us to think about what value really means. The solution lies in the difference between total utility and marginal utility. Water is essential, but it is also abundant in most places. Once your basic need for water is met, Each extra glass adds less to your well-being. Diamonds, on the other hand, are rare and difficult to obtain. Their scarcity makes each one highly valuable, even though their practical use is small. The paradox of value highlights the difference between what is essential in principle and what is scarce in practice. It reveals that value is not absolute. It depends on context, scarcity, and human desire. Beyond economics, this paradox carries a moral lesson. It forces us to see that society often rewards luxury more than necessity, and that markets don't always reflect the true importance of things. It challenges us to think critically about wealth, scarcity, and fairness in human life. At its core, the paradox of value teaches us that value is not just about survival, it's about perception. And perception, driven by rarity and desire, can sometimes put glitter above life itself. The arrow of time paradox. Everywhere we look, time seems to flow in one direction, forward. We remember the past but not the future. We grow older, never younger. A broken glass may shatter on the floor, but it never reassembles itself. Yet when scientists look at the laws of physics, they find something strange. The fundamental equations don't care about direction. Whether time runs forward or backward, the math works the same. So, why do we experience time as an arrow pointing one way? This is the arrow of time paradox. It challenges us to explain why the universe has a clear past and future when the rules that govern it appear perfectly symmetrical. One possible explanation lies in entropy, the measure of disorder. According to the second law of thermodynamics, entropy always increases. That's why heat spreads out, why things decay, why the past looks ordered while the future looks uncertain. The arrow of time, some say, is simply the arrow of increasing entropy. But this raises new questions. Why did the universe start in such an ordered, low-entropy state to begin with? And if the laws of physics are reversible, why do we only perceive one direction? The paradox forces us to confront the mystery of time itself. Is time something fundamental, or is it an illusion created by the way we experience entropy? The arrow of time paradox doesn't just belong to physics. It touches our deepest human experience. We live caught between a past we cannot change and a future we cannot see. It reminds us that time, one of the most familiar things in our lives, may be the greatest mystery of all. The information paradox. The information paradox often refers to a deep conflict in physics, closely tied to black holes. It begins with a simple rule. In quantum mechanics, information cannot be destroyed. The universe always keeps the books, even if matter changes form. But black holes seem to defy this law. When something falls into a black hole, all its details, its structure, its information, vanish behind the event horizon. If the black hole eventually evaporates, as Stephen Hawking suggested, the information appears to be lost forever. That would mean the universe has erased part of its own history, something quantum mechanics says should be impossible. The paradox has haunted physicists for decades. Some argue that information is somehow encoded on the surface of the black hole, a principle called the holographic theory. Others suggest that Hawking radiation carries the information out in ways we don't yet understand. Still others think we may need a radical new theory that unites gravity and quantum physics to solve the puzzle. Beyond science, the information paradox speaks to something human. It raises questions about memory, permanence, and loss. If the universe itself risks forgetting, what does that say about us, fragile creatures trying to hold on to meaning in a world of constant change? At its heart, this paradox asks whether reality is ultimately consistent, or whether even the universe has limits to what it can preserve. It reminds us that some mysteries are not just unanswered, they may be waiting to rewrite everything we think we know. The paradox of choice. In modern life, we often believe that more options mean more freedom and more happiness. But the paradox of choice suggests the opposite. When faced with too many options, people often feel overwhelmed, anxious, and less satisfied with whatever they pick. Imagine standing in front of a supermarket shelf with 50 different kinds of cereal. On the surface, this seems like abundance. But the more options you face, the harder the decision becomes. You start worrying, what if I choose the wrong one? What if the other tastes better? Even after deciding, you may feel regret, convinced another choice would have been better. The paradox of choice shows that freedom without limits can backfire. A few choices empower us, but too many can paralyze us. Psychologists have found that people often report greater happiness when given fewer options, because they feel more confident and less burdened by regret. This paradox reaches far beyond cereal aisles. It affects careers, relationships, technology, and even identity. In a world overflowing with possibilities, from endless online shopping to infinite entertainment, choice can become a trap. The lesson is not that choice is bad, but that balance is key. The paradox of choice reminds us that sometimes less is more, and that freedom comes not from infinite options, but from clarity, purpose, and the courage to choose without regret. The barbershop paradox. The barbershop paradox, unlike the barber paradox, comes from a logical puzzle created by Carrol. Imagine a small village where there are three men, Allen, Brown, and Carr. The barber knows that at least one of them is always in the barbershop, but the barber also knows that if Allen is not there, then Brown must be there. If Brown is not there, then Carr must be there. Yet strangely, when you put all this information together, it seems possible that none of them are in the barbershop at all, which contradicts the very first fact. The paradox arises because of the way conditional statements interact. Each if-then rule seems reasonable on its own, but when combined, they create a logical tangle that seems to deny the original assumption. Carrol used this puzzle to show how even simple rules can produce contradictions if they aren't carefully structured. At its core, the barbershop paradox is about the fragility of logic. It reminds us that reasoning is only as reliable as the assumptions we build it on. If we don't examine how rules connect to one another, we can end up trapped in contradictions. This paradox reflects real life too. Laws, contracts, and social rules can sometimes conflict in ways that make it impossible to satisfy all of them at once. The barbershop paradox teaches us that even logic, the most trusted tool for clarity, can become tangled when conditions overlap. Galileo's paradox. Galileo Galilei, the great scientist, noticed something puzzling about infinity. He compared two sets of numbers, the natural numbers, 1, 2, 3, 4, and the perfect squares, 1, 4, 9, 16. At first glance, there should be fewer perfect squares than natural numbers, because squares are only a part of the whole set. But here's the twist. Galileo showed that you can match every natural number with exactly one square, 1 with 1, 2 with 4, 3 with 9, and so on. That means the two sets are the same size, infinite. So, are there fewer squares than numbers, or the same number? Both answers seem true, depending on how you look at it. This is Galileo's paradox. It reveals the strange nature of infinity, where our everyday ideas of bigger and smaller break down. This paradox led to deeper studies of infinity by later mathematicians like Georg Cantor, who showed that some infinities are actually bigger than others. But Galileo was one of the first to point out that infinity does not follow the same rules as finite numbers. On a deeper level, Galileo's paradox teaches us humility. It reminds us that our intuition, shaped by finite experience, cannot easily grasp the infinite. What feels obvious, that a part is smaller than the whole, may collapse when applied to infinity. The paradox invites us to step beyond common sense and explore the mysteries of mathematics that stretch beyond imagination. The Infinite Hotel. Hilbert's Hotel. Picture a hotel with an infinite number of rooms, each already occupied by a guest. A new traveler arrives and asks for a room. At first, it seems impossible. The hotel is full. But the manager smiles and says, "No problem." He simply asks each guest to move from room 1 to room 2, from room 2 to room 3, and so on. This frees up room 1 for the new guest. Now imagine an infinite number of new travelers arrive all at once. Again, the hotelier has a trick. He asks the current guests to move to room 2, room 4, room 6, and so on, leaving all the odd-numbered rooms empty for the newcomers. The paradox is that the hotel is both completely full and yet always has room for more. Hilbert's Hotel, as it's called, illustrates the strange and counterintuitive nature of infinity. In the finite world, full means no space left. But in the infinite world, fullness and emptiness can coexist in bizarre ways. This paradox challenges us to rethink the very idea of space and quantity. It shows why infinity cannot be treated like an ordinary number. It behaves in ways that break intuition. Philosophers and mathematicians use Hilbert's Hotel to explore ideas about the universe, mathematics, and even theology, since it touches on the idea of the infinite in reality. On a deeper level, the Infinite Hotel makes us ask, if infinity is this strange in mathematics, what does it mean when we apply it to the cosmos? Could the universe itself be infinite? And if so, what hidden mysteries might it contain? The Banach Tarski paradox. The Banach Tarski paradox is one of the strangest results in mathematics. So strange that it almost feels like magic. It says that if you take a solid ball, like a sphere, you can cut it into a finite number of pieces, move those pieces around, and reassemble them into two balls that are exactly the same size as the original. In other words, you can duplicate a ball out of nothing. At first glance, this seems impossible. How can you take one thing and, without stretching or adding anything, suddenly have two? It sounds like breaking the laws of physics, but the paradox is purely mathematical. The trick lies in the way the ball is divided. The pieces are not normal chunks we can imagine. They are infinitely complicated, made possible by the strange properties of infinity and set theory. This paradox challenges our understanding of volume, matter, and space. In the real world, you could never actually perform this process because physical matter is made of atoms, not infinite mathematical points. But in the abstract world of pure mathematics, the Banach Tarski paradox shows that our intuitive ideas of size and volume fall apart when infinity is involved. On a deeper level, this paradox makes us rethink the connection between mathematics and reality. Math tells us something logically consistent but physically impossible. Does that mean math is detached from the real world, or does it mean reality is stranger than we think? The Banach Tarski paradox is a reminder that infinity is not just big, it's weird. It bends our understanding of space itself, turning one ball into two, and showing that the rules of the infinite don't always play by the logic of the finite. The Ross-Littlewood paradox. The Ross-Littlewood paradox is a thought experiment involving an infinite process. Imagine a jar and an infinite number of balls numbered 1, 2, 3, and so on. At the first step, you put balls 1 through 10 into the jar and remove ball number 1. At the next step, you add balls 11 through 20 and remove ball number 2. You keep repeating this forever, adding 10 new balls and removing one specific ball each time. Here's the paradox. After an infinite number of steps, how many balls are left in the jar? On one hand, it looks like infinitely many because you keep adding more and more balls. But on the other hand, every specific ball will eventually be removed at some step, meaning no ball can ever remain. So is the jar full of infinitely many balls, or completely empty? Both answers seem true, and both seem impossible. This paradox reveals the strange behavior of infinity and limits. It shows how infinite processes don't always behave the way we expect. Depending on how we interpret the sequence, we can end up with totally different outcomes: full, empty, or something in between. The Ross-Littlewood paradox teaches us that infinity is not a number we can handle like the rest. It's a process, a horizon, something that changes depending on how you approach it. It reminds us that infinity can produce contradictions that stretch beyond our everyday logic. At a deeper level, it echoes human life. We often imagine endless possibilities or infinite time, but the paradox shows how infinity slips through our grasp. It teaches us that not everything infinite has a simple conclusion. Thompson's lamp. Thompson's lamp is a paradox about infinity and time. Imagine a lamp with a switch. At noon, you turn it on. After 30 seconds, you turn it off. After 15 more seconds, you turn it on again. Then after 7.5 seconds, you turn it off. Each time, the interval is cut in half, so the switch is flipped infinitely many times before 1 p.m. arrives. Now here's the question. At exactly 1 p.m., is the lamp on or off? The paradox is that there's no clear answer. Every step in the process is well defined. On, off, on, off. But when the infinite sequence ends, there is no final state. The lamp should be in one of the two states, but the process never settles on either. Thompson's lamp highlights the strange consequences of trying to perform infinite actions in a finite time. It shows that infinity is not just about numbers, but about processes that defy completion. It also reveals the limits of human reasoning. Our minds want to force an answer, but the paradox shows that sometimes the answer doesn't exist. This paradox has been used in philosophy to explore the concept of supertasks. completing infinitely many actions in a finite span. It raises questions about motion, time, and reality itself. Can infinity actually happen in the real world, or is it only a feature of abstract thought? At its core, Thompson's lamp is not about light or switches. It's about the tension between the finite and the infinite, and the mysteries that emerge when we try to push logic into realms it was never meant to go. The uncountability paradox. The uncountability paradox arises from the strange world of infinity in mathematics. We know how to count natural numbers, 1, 2, 3, and so on, forever. Infinity here feels like a never-ending list. But when mathematicians like Georg Cantor studied infinity more deeply, they discovered that not all infinities are the same. Some are bigger than others, and that's where the paradox begins. Consider the real numbers, which include not just whole numbers, but fractions and decimals, like 1.5, 2.345, or pa. Cantor proved that you cannot list all real numbers in a sequence the way you can with natural numbers. No matter how you try, there will always be a number left out. This means the set of real numbers is uncountably infinite, a larger infinity than the countable infinity of natural numbers. The paradox lies in our intuition. Infinity is already beyond comprehension, so how can there be something bigger than infinity? To the human mind, infinity feels like the maximum, the ultimate. Yet mathematics shows us that infinity comes in levels, some so vast that they make others look small in comparison. The uncountability paradox forces us to question what size means when applied to infinite sets. It also reminds us that human intuition, shaped by the finite world, breaks down when it confronts the infinite. What feels like contradiction is actually truth, but truth that is almost too big to grasp. The Gabriel's horn paradox, Gabriel's horn, also called Torricelli's trumpet, is a mathematical shape with impossible properties. Imagine taking the curve of one bar corners and revolving it around an axis, creating a horn that stretches infinitely long but narrows forever toward a point. The paradox comes when you measure it. Gabriel's horn has a finite volume but an infinite surface area. In simple terms, you could fill the horn with paint. It wouldn't take an infinite amount because the volume is limited. But if you then tried to paint the inside surface, you would need an infinite amount of paint because the surface area is endless. This paradox plays with our understanding of geometry, space, and infinity. How can something be filled completely but never fully covered? It feels like a contradiction, yet mathematically it's perfectly consistent. The horn demonstrates how infinite processes can create shapes that defy ordinary intuition. Philosophically, Gabriel's horn touches on the tension between the finite and the infinite. It shows how something can be endless in one respect but bounded in another, depending on how you measure it. It challenges the way we think about wholeness and completion. Beyond math, Gabriel's horn is a metaphor for human curiosity itself. The more we try to grasp the infinite, the more we realize that our tools, like paint on a surface, can never quite cover the full expanse. The paradox of the cone. The paradox of the cone comes from ancient Greek philosophy, particularly from Aristotle. Imagine a cone standing upright. Now, slice it horizontally through the middle. The top surface is a circle, and the bottom surface is also a circle. But what about the line where the two halves meet? Is it a circle like the rest of the cone's cross-sections, or is it just a single flat line where the two circles touch? This question creates a paradox because it exposes the difficulty of defining boundaries. If the meeting point is a circle, then we would be saying that two different circles occupy the exact same space, which feels wrong. But if it's just a line, then we've changed the nature of the cone's surface abruptly at that point, which also feels wrong. The paradox of the cone reveals the problem of continuity in geometry. Where does one shape end and another begin? Is there a sharp boundary, or are boundaries always an illusion created by perspective? On a deeper level, this paradox goes beyond geometry. It's about the limits of categorization and definition. In life, as in geometry, we often want clear lines, beginnings and endings, boundaries and divisions. But reality may not work that way. The world is full of transitions and gradients, where one thing fades into another without a clear break. The paradox of the cone teaches us that our need for sharp answers can clash with the smooth, continuous nature of reality. It reminds us that sometimes the most important truths lie in the blurry spaces where definitions collapse. The measure problem. The measure problem arises in modern cosmology, especially in theories about the multiverse. Imagine that our universe is not the only one. Instead, there are infinitely many universes, each with different laws, constants, or outcomes. This idea may explain some mysteries of physics, but it creates a new one. If there are infinitely many universes, how do we measure probability? For example, if there are infinite universes where you win the lottery, and also infinite universes where you lose, then what is the true probability of winning? In normal math, probability is about ratios of outcomes, but infinity makes those ratios impossible to define clearly. The paradox is that with an infinite multiverse, almost anything that can happen does happen, not just once, but infinitely many times. This creates chaos for prediction. If every possibility is realized, then how can we say what's likely? Without a way to measure probabilities in an infinite set, cosmology struggles to make sense of its own predictions. On a deeper level, the measure problem reveals the strangeness of infinity when applied to reality. It suggests that the multiverse may be beyond human comprehension, not because it's too big, but because our very tools for understanding, like probability and measure, collapse in the face of endlessness. Philosophically, it reminds us of the limits of knowledge. We crave certainty, but the universe may refuse to be measured in the ways we expect. The measure problem shows that even science, when it stares into the infinite, finds itself at the edge of paradox. The Boltzmann brain paradox. The Boltzmann brain paradox comes from statistical mechanics and cosmology. Ludwig Boltzmann, a 19th century physicist, explained the universe's order by probability. In a sea of chaos, he argued, it's not impossible for order to arise by chance, like dice randomly landing in perfect sequence. Our universe, he suggested, could just be a rare fluctuation in an otherwise disordered cosmos. But here's where the paradox emerges. If the universe is infinite and time is eternal, then the most likely fluctuation is not a vast, orderly cosmos like ours, but something much smaller. A single brain, complete with false memories, spontaneously popping into existence out of randomness. Such a Boltzmann brain would briefly exist, believe itself to be a real person in a real universe, and then vanish back into chaos. The paradox is chilling, because it suggests that it's far more likely we are Boltzmann brains than beings living in a stable, long-lasting universe. If probability favors the smallest possible fluctuation, then our entire reality might be nothing but a fleeting hallucination inside a brain born from randomness. This paradox strikes at the heart of identity, existence, and trust in perception. How do we know the universe is real and not just a short-lived illusion? Science relies on assumptions of stability, but the Boltzmann brain paradox whispers that stability may be the unlikely path. It forces us to confront the possibility that our sense of reality is fragile. And while most physicists argue that a good theory of the universe must avoid this paradox, the very fact that it exists shows how probability and infinity can lead to terrifying, mind-bending conclusions. The Gibbs paradox. The Gibbs paradox arises in thermodynamics and the study of entropy. Imagine you have two containers of gas. In one, there are molecules of oxygen, in the other, molecules of nitrogen. You remove the barrier between them, and the gases mix together. Entropy, or disorder, increases, as expected. Now, imagine repeating the experiment, but this time both containers hold the exact same gas, like oxygen on both sides. When the barrier is removed, the molecules still spread out and mix, but this time we say entropy doesn't increase. Why not? Physically, the motion looks the same, but thermodynamics treats the mixing of identical gases as if nothing really happened. The paradox is that entropy seems to depend not just on what happens physically, but on how we label the particles. If the gases are different, entropy rises. If they are identical, entropy doesn't. But since particles of gas are fundamentally indistinguishable, why should entropy care? The Gibbs paradox challenges the boundary between physics and information. It shows that our definitions of order and disorder are not just about matter, but about how we describe and distinguish it. Entropy is as much about knowledge as it is about physical systems. On a deeper level, this paradox reminds us that reality is filtered through perspective. What looks like chaos to one observer may look like order to another. It teaches us that even in the precise world of physics, human concepts like difference and sameness shape the way we measure the universe. The Gibbs paradox reveals that the universe is not just made of particles, it's also made of the stories we tell about them. Parando's paradox. Parando's paradox is one of the strangest ideas in probability and game theory. Imagine you are playing two games. Game A is simple. It's rigged against you. Every time you play, you lose a little more than you win. Game B is also unfair. The odds shift based on your current amount of money, but in every setup, the game still leans against you. Both games, on their own, guarantee you will eventually lose. But here's the shocking twist. If you alternate between the two losing games in a certain sequence, suddenly you start winning. Two guaranteed losers combine to create a winner. This is Parando's paradox. It challenges our intuition about fairness, luck, and strategy. We assume that combining two bad options should never make a good one, but this paradox shows that outcomes are not always simple sums of their parts. The order, the timing, and the interaction between the games create unexpected results. On a deeper level, Parando's paradox mirrors real life. Sometimes, alternating between two difficult strategies or combining two wrongs can lead to success. It's a reminder that progress doesn't always come from steady gains, but from carefully balancing risks and losses. Philosophically, it teaches us that the path to winning isn't always straightforward. Sometimes, what seems like guaranteed failure can hide the seeds of victory, if we know how to shift perspective and embrace complexity. The St. Petersburg paradox. The St. Petersburg paradox is a classic puzzle in probability and economics. Imagine a game where a coin is flipped until it lands heads. If the first head appears on the first flip, you win $2. If it comes on the second flip, you win $4. If it's on the third flip, you win $8. Each time, the prize doubles. Since the coin could, in theory, flip tails forever, the possible winnings are unbounded. Now, if you calculate the expected value of this game, the result is infinite. That means a rational person should be willing to pay any amount of money to play. But in reality, most people would only pay a modest amount, maybe $10-20. No one would pay their life savings for the chance to play. This is the St. Petersburg paradox. The math says the game is infinitely valuable, but human intuition says it isn't. The paradox reveals the limits of expected value as a measure of decision-making. It shows that people value outcomes based not just on probabilities, but on utility. The real-world impact of money, which is not linear. Winning 1 million isn't 1,000 times better than winning 1,000 to most people, because human happiness doesn't scale infinitely with wealth. On a deeper level, the St. Petersburg paradox challenges our understanding of risk, reward, and rationality. It reminds us that human beings are not abstract calculators, but living creatures with limits, instincts, and emotions. The paradox is a bridge between mathematics and psychology, showing how numbers and human nature often collide. The Ellsberg paradox. The Ellsberg paradox deals with uncertainty and decision-making under risk. Imagine two urns. Urn A contains exactly 50 red balls and 50 black balls. Urn B also has 100 balls, but you don't know the exact mix of red and black. Now, suppose you have to bet on drawing a red ball. Most people choose urn A, where the odds are clear, rather than urn B, where the odds are unknown. But here's where it gets strange. If you change the bet to betting on a black ball, people again choose urn A. Logically, this makes no sense. If you reject urn B for red, you should prefer it for black. Yet people avoid urn B in both cases. This is the Ellsberg paradox. Human beings prefer known risks over unknown risks, even when the math suggests the outcomes should balance out. It reveals our deep aversion to ambiguity. The paradox has shaped economics and psychology, showing that people don't act according to rational probability theory. Instead, they rely on intuition, comfort, and fear of the unknown. On a deeper level, the Ellsberg paradox speaks to human psychology itself. We crave certainty, even if it means missing opportunities. We would rather face a fair gamble we understand than an uncertain gamble that might be better. It shows that rationality is not the same as peace of mind. This paradox teaches us that uncertainty, not risk, is often the true enemy of human decision-making. It reveals why people cling to the known, even in a world where the unknown may hold greater rewards. The Allais paradox. The Allais paradox is a challenge to classical economic theory, particularly the idea that humans make decisions rationally when faced with risk. Maurice Allais, a French economist, designed an experiment with two choices. In the first choice, you can pick between option A, a guaranteed $1 million, option B, a 10% chance to win $2.5 million, an 89% chance to win $1 million, and a 1% chance to win nothing. Most people pick option A, preferring the certainty of $1 million over a gamble, even though the gamble could give them more. But in the second choice, you can pick between option C, an 11% chance to win $1 million and an 89% chance to win nothing. Option D, a 10% chance to win $2.5 million and a 90% chance to win nothing. Here, most people choose option D, chasing the bigger prize even though the odds are worse. The paradox is that these preferences contradict the expected utility theory, which says rational people should be consistent. If you prefer certainty in the first scenario, logic says you should prefer the safer bet in the second one too. But people don't, they switch. The Allais paradox shows that humans are not perfectly rational calculators. We value certainty far more than probability when the stakes are high, but we also take risks when there's nothing guaranteed. It reveals that our psychology, not just mathematics, shapes our choices. On a deeper level, this paradox tells us something profound about human nature. We are driven as much by emotions, fear of loss, thrill of gain, as by reason. It reminds us that rationality is an ideal, not always a reality. The friendship paradox is one of those counterintuitive truths that feels like a trick, but it's mathematically sound. It says that, on average, most people's friends have more friends than they do. At first, this sounds impossible. How could your friends be more popular than you, on average? But the explanation lies in statistics. Popular people, those with many friends, are more likely to show up in the friend lists of others. So when you look at your friends, the sample is biased toward more popular individuals. The paradox is not just about social networks. It reveals how perception is skewed by structure. It makes people feel less connected than they actually are, because they compare themselves to highly connected individuals who dominate the averages. In real life, the friendship paradox has been observed in schools, workplaces, and even online platforms. It explains why people often feel lonelier or less popular than others, even when they are not. It's a paradox of perception, showing how our view of ourselves is distorted by the social web around us. On a deeper level, this paradox teaches a life lesson. The way we compare ourselves to others is often unfair and misleading. Just as in networks, where averages are weighted toward the extremes, in life, we often compare ourselves to people who are outliers in success, wealth, or influence. The friendship paradox reminds us that our perspective is biased, and that our worth cannot be measured by skewed comparisons. Brace's paradox deals with traffic flow, and it shows that sometimes adding more roads to a network can actually make traffic worse, not better. Imagine a city where two routes connect the same start and end point. Traffic spreads out between them, and the system runs smoothly. Now the city builds a new shortcut that looks like it will save time. Rationally, drivers start using it, since each person is trying to minimize their own travel time. But as more drivers take the shortcut, congestion builds up, and the entire system slows down. In the end, everyone is worse off than before the new road was added. This is Brace's paradox. When individuals act in their own self-interest, the collective outcome can be worse. It's a real-world example of how optimization at the individual level does not always lead to optimization at the group level. The paradox appears not just in traffic, but in networks of all kinds, communication systems, energy grids, even social dynamics. Sometimes, removing resources rather than adding them can actually improve performance. At a deeper level, Brace's paradox reflects the tension between selfishness and cooperation. It shows that systems work best when individuals think not just of themselves, but of the collective whole. It reminds us that efficiency is not always about more, but about balance, coordination, and sometimes restraint. Jevons paradox. The Jevons paradox is a surprising insight from economics and environmental studies. William Stanley Jevons, a 19th century economist, noticed something strange about coal consumption in Britain. As technology improved, coal-powered engines became more efficient. Logic suggests that more efficiency should reduce coal usage, but the opposite happened. coal consumption skyrocketed. Why? Because greater efficiency made coal cheaper and more useful, which encouraged people to use it in more industries and on a larger scale. Instead of conserving resources, efficiency led to even more consumption. This is the Jevons paradox. When you make something more efficient, overall usage can actually increase rather than decrease. It's a warning against the naive belief that technology alone can solve environmental or resource problems. For example, more fuel-efficient cars might lower fuel use per mile, but if they encourage people to drive more, total fuel consumption can still rise. The paradox is not just about coal or energy. It reflects a deeper truth about human behavior. When something becomes easier or cheaper, demand often grows faster than efficiency improves. This paradox forces us to question whether progress is always as green or sustainable as it seems. On a broader level, the Jevons paradox teaches us that solutions to big problems, like climate change or resource scarcity, must consider human behavior as much as technology. Efficiency alone cannot save us if it only feeds our appetite for more. The green paradox. The green paradox is another challenge in environmental economics. It suggests that well-meaning policies designed to slow down climate change may sometimes make the problem worse. For example, if governments announce strict carbon taxes or bans on fossil fuels in the future, resource owners might react by accelerating extraction and burning now, before those policies take effect. Instead of reducing emissions, the announcement causes a surge in emissions today. The paradox is unsettling because it shows how intentions can backfire when they don't account for economic incentives. A policy aimed at saving the planet might push industries to act in ways that speed up damage. At a deeper level, the green paradox highlights the complexity of human systems. Environmental solutions are not just about science, but about psychology, markets, and timing. It reveals how interconnected everything is, how a good idea on paper can have unintended consequences in reality. This paradox reminds us that solving global crises requires more than good intentions. It requires careful anticipation of human behavior, economic pressure, and political response. The green paradox warns us that in trying to save tomorrow, we must be careful not to make today worse. The Abilene paradox. The Abilene paradox is a psychological and social paradox that reveals the power of group dynamics. Imagine a family sitting on a porch in Texas on a hot day. One person suggests, "Let's drive to Abilene for dinner." No one really wants to go. It's far, the drive is uncomfortable, and the food isn't great, but each person, thinking the others want to go, agrees. They all pile into the car, drive hours in the heat, eat an unsatisfying meal, and return exhausted. Only then do they realize none of them wanted to go in the first place. This is the Abilene paradox. Groups sometimes make collective decisions that no individual actually wants, because everyone assumes it's what others desire. Fear of standing out, avoiding conflict, or misunderstanding others' preferences drives people to go along with choices they secretly oppose. The paradox is not just about road trips. It plays out in businesses, governments, and even friendships. Teams may pursue strategies no one believes in, simply because each member is afraid to voice dissent. Families may make plans that make everyone unhappy, all because no one wants to disrupt harmony. On a deeper level, the Abilene paradox teaches us about the dangers of silence and assumption. It shows how communication breakdowns can lead to outcomes that satisfy no one. It reminds us that leadership and honesty are not about going along with the crowd, but about voicing truth even when it feels uncomfortable. The Abilene paradox is a mirror to society itself, revealing how often we march toward destinations none of us actually chose. The paradox of hedonism, sometimes called the pleasure paradox, asks a simple but unsettling question. Can you really find happiness by directly chasing it? On the surface, it seems obvious. If pleasure is the goal of life, then seeking pleasure should bring it. But the paradox shows that the more directly you pursue happiness, the more it slips away. Think about it. If you focus only on being happy, every small disappointment becomes magnified. Every moment of boredom feels like failure. Happiness, instead of being gained, becomes a constant worry. In the end, people who obsess over finding joy often feel more miserable than those who focus on other things. The paradox reveals that happiness works indirectly. We find joy not by hunting it down, but by pursuing meaning, relationships, creativity, or growth. Pleasure is a byproduct of living well, not the main course. Like chasing a butterfly, the harder you run after it, the further it flies. But if you sit quietly, it might land on your shoulder. On a deeper level, the paradox of hedonism challenges our modern obsession with happiness. It reminds us that joy cannot be bought, forced, or demanded. It teaches that fulfillment comes from forgetting yourself in the act of living, not from making happiness itself the ultimate goal. The paradox of tragedy. The paradox of tragedy asks, why do people enjoy watching or reading tragedies? Stories that make them cry, break their hearts, or fill them with grief. If humans naturally seek pleasure and avoid pain, then tragic art should repel us. And yet, from ancient Greek plays to modern films, we are drawn to stories of loss, betrayal, and suffering. This paradox puzzled philosophers for centuries. Aristotle suggested that tragedy gives us catharsis, a cleansing of emotions. By watching characters suffer, we purge our own fear and pity in a safe environment. Others argue that tragedy helps us confront truths about life that we avoid in daily living. On another level, tragedy allows us to experience powerful emotions without real-world consequences. We can mourn for fictional characters while knowing we'll return to safety afterward. This emotional intensity makes us feel more alive. The paradox of tragedy reminds us that pain is not the opposite of pleasure. It can be part of what makes life meaningful. Sometimes, sorrow in art reveals truths about humanity that joy alone cannot express. We don't enjoy suffering itself, but the beauty, depth, and connection that suffering in art awakens in us. The paradox of fiction digs even deeper into the mystery of emotions. It asks, how can we feel real emotions, fear, sadness, love, for characters and stories we know are not real? Why do we cry when a fictional hero dies, or feel afraid of a monster we know is only pixels on a screen? On the surface, this seems irrational. To feel fear, we normally need to believe the danger is real. To feel sadness, we normally need to believe the loss is real. But when it comes to fiction, we suspend disbelief just enough to engage emotionally, even while knowing it's just a story. This paradox shows the complexity of the human mind. Our imagination is so powerful that it can trick our emotional system into responding as if fiction were real. Stories bypass logic and go straight to the heart. On a deeper level, the paradox of fiction reveals why storytelling is central to human culture. Fiction allows us to practice emotions, explore moral dilemmas, and connect to universal truths in a safe, symbolic space. It shows that truth is not always about literal reality. Sometimes the deepest truths live in stories we know are not real. The paradox of fiction reminds us that imagination is not an escape from life, but a mirror of it. We cry for things that never happened because in some way they speak to what it means to be human. The paradox of suspense. The paradox of suspense asks, how can we feel suspense when we already know the outcome of a story? Think about it. People rewatch movies, reread novels, or revisit shows they've seen before. They know exactly who lives, who dies, and how the story ends. And yet, they still feel tense, nervous, or even on the edge of their seats, as if they were seeing it for the first time. Logically, suspense should depend on uncertainty. If you know the ending, there's no uncertainty, but the human mind doesn't work that way. Even with full knowledge, our emotions respond to the moment. Our bodies react to the danger on screen, the music, the pacing, and the stakes, almost as if our minds forget what's coming. This paradox reveals the strange divide between intellect and emotion. Our rational brain may know the outcome, but our emotional brain lives in the present, reacting as if the story were unfolding for the first time. On a deeper level, the paradox of suspense shows how storytelling is not just about information, but about experience. We don't rewatch stories to learn the ending. We rewatch to relive the emotional journey. Suspense isn't destroyed by knowledge. It's recreated every time, because our emotions play by different rules than logic. The paradox of horror. The paradox of horror asks, why do people willingly seek out stories that terrify them? Horror movies, haunted houses, ghost stories. These experiences fill us with fear, disgust, or dread, yet millions of people flock to them for entertainment. If fear is an unpleasant emotion, why do we pay to feel it? One answer is that horror provides a safe space to explore fear. In real life, fear can be overwhelming and dangerous, but in a movie theater, the monsters can't hurt us. We can experience terror while knowing, deep down, we are safe. This mix of danger and safety creates a thrill. Another explanation is that horror satisfies curiosity. Humans are drawn to the unknown, the forbidden, the dark corners of existence. Horror lets us peek into those shadows without stepping into real danger. It's a way to confront the unthinkable while staying in control. On a deeper level, the paradox of horror reveals something primal about humanity. Fear reminds us we are alive. It shakes us out of numbness and forces us to confront mortality, danger, and the fragility of life. Horror may repel us with its images, but it also awakens us to truths we cannot ignore. The paradox teaches us that fear is not only an emotion to avoid, it can be an emotion to embrace when balanced with safety and meaning. Horror is both repulsive and magnetic because it touches the deepest layers of our psychology. The Euthyphro dilemma. The Euthyphro dilemma comes from Plato's dialogue Euthyphro, and it raises a timeless question about morality and the divine. Socrates asks, "Is something good because the gods command it, or do the gods command it because it is good? If something is good simply because the gods command it, then morality seems arbitrary. Anything, no matter how cruel, could be good if commanded by divine authority. But if the gods command something because it is already good, then morality exists independently of divine will, meaning the gods are not the source of goodness, but followers of it. This creates a paradox for religious and moral philosophy. If morality depends entirely on divine command, it loses its objectivity. But if morality exists apart from the divine, then divinity is not the ultimate foundation of ethics. The Euthyphro dilemma is powerful because it forces us to ask where morality truly comes from. Is it written into the fabric of the universe? Is it created by God, or is it something humans construct? On a deeper level, this paradox shows the tension between authority and reason. It teaches us that true morality must be more than obedience. It must involve understanding, reflection, and choice. Whether we ground morality in religion, reason, or humanity, the Euthyphro dilemma reminds us that the question of why good is never simple. The omniscience paradox asks, what does it mean for a being to know everything? At first, omniscience sounds simple, total knowledge of all truths. But when you push the concept to its limits, contradictions appear. For example, can an omniscient being know what it feels like not to know something? If they truly know everything, they cannot experience ignorance. But if they cannot experience ignorance, then there is something they don't know, namely, what it feels like to lack knowledge. Similarly, can an omniscient being know future free choices? If the future is already known, then it seems our choices are fixed, which threatens the very idea of free will. The paradox grows deeper when we consider self-knowledge. If an omniscient being knows every detail of their own future thoughts, do they have the freedom to think otherwise? Or are even their thoughts predetermined? This paradox challenges theology, philosophy, and metaphysics alike. It forces us to ask whether infinite knowledge is possible, or whether omniscience is an idea that collapses under its own weight. On a human level, the omniscience paradox reminds us of our limits. We long to know everything, to understand the world completely. But maybe the mystery of life isn't a flaw. Maybe it's what makes freedom, growth, and discovery possible. Perhaps ignorance isn't weakness, but the very condition that makes life meaningful. The paradox of foreknowledge. The paradox of foreknowledge is closely tied to questions of fate, prophecy, and free will. It asks, if someone knows the future with absolute certainty, can that future still be changed? Imagine a prophet who tells you that tomorrow at noon, you will drink a glass of water. If the prophecy is true, then no matter what you try, resisting, hiding, even smashing every glass in sight, somehow you will still end up drinking water. If the prophecy is false, then the foreknowledge wasn't really knowledge at all. This paradox puts freedom and certainty into conflict. If the future can be known, then it must already be fixed. But if it's fixed, then human choice seems like an illusion. On the other hand, if humans truly have free will, then the future is not fixed, and therefore cannot be perfectly known. The paradox of foreknowledge raises profound questions about time. Is the future already written, waiting to be revealed, or is it open, unfolding only as choices are made? On a deeper level, this paradox forces us to confront our relationship with destiny. We crave certainty, but certainty may cost us freedom. We crave freedom, but freedom may cost us certainty. The paradox of foreknowledge is not just about prophecy, it's about the mystery of whether we are passengers on a scripted journey or authors of our own fate. The doomsday argument. The doomsday argument is a modern paradox that combines probability with humanity's future. It starts with a simple question. Given what we know about ourselves, what are the odds that humanity is close to its end? The argument goes like this. Imagine every human being is assigned a number based on when they are born. The first human is 1, the second is 2, and so on. Now, consider yourself. You are probably not among the very first humans to ever exist, but also not among the very last. Statistically, you're likely somewhere in the middle. If that's true, then the total number of humans who will ever live cannot be astronomically larger than the number who have already lived. In other words, humanity's timeline may be much shorter than we like to think. This reasoning suggests that the end of humanity may be closer than our optimism allows. It doesn't predict an exact date, but it implies that expecting billions of future generations may be unrealistic. The paradox is unsettling because it uses probability, not prophecy, to hint at doom. It challenges our assumptions about survival, progress, and the destiny of our species. On a deeper level, the doomsday argument reveals our fear of fragility. It reminds us that civilizations are not immortal, and that humanity's story, like every story, may have an end. But it also challenges us. Even if the argument points to doom, what will we do with the time we have? The paradox forces us to face mortality not only as individuals, but as a species. The simulation paradox. The simulation paradox asks, if our universe is a computer simulation, could we ever truly know? And if we discovered the truth, what would it mean for our reality? Philosopher Nick Bostrom famously argued that one of three things must be true. Either civilizations never reach the point of creating simulations of conscious beings, or they reach that point but choose not to run them, or they do run them, in which case the number of simulated beings would vastly outnumber real beings, making it statistically more likely that we are simulations. Here's where the paradox begins. If we are in a simulation, then everything we know, physics, time, consciousness, is a construct. But if we try to prove we're in a simulation, any evidence we find could itself be part of the simulation, planted by its designers. We'd be trapped in a hall of mirrors, unable to confirm or escape the illusion. The paradox deepens when we ask, if we are simulated, do our choices matter, or are we just programmed responses? But then again, how different is that from debates about free will in a physical universe governed by laws of nature? On a deeper level, the simulation paradox forces us to rethink meaning itself. Whether reality is base level or simulated, our experiences feel real to us. Pain hurts, joy uplifts, love transforms. The paradox reminds us that truth is not only about what reality is, but about how we live within it. Schrödinger's cat. Schrödinger's cat is perhaps the most famous paradox in quantum physics. Imagine a cat in a sealed box. Inside the box is a radioactive atom with a 50% chance of decaying in an hour. If it decays, it triggers poison that kills the cat. If it doesn't, the cat lives. Quantum mechanics tells us that until we open the box and observe, the atom exists in a superposition, both decayed and not decayed, which means the cat too is both dead and alive at the same time. This paradox was not meant to suggest cats are literally undead. Schrödinger created it to show how absurd quantum theory sounds when applied to everyday objects. But it perfectly captures the strangeness of the quantum world, where particles can exist in multiple states at once until observed. The paradox forces us to ask, what role does observation play in reality? Does the universe decide outcomes only when someone looks? Or is reality branching into multiple possibilities, with one cat alive in one universe and another dead in a parallel one? On a deeper level, Schrödinger's cat challenges our entire sense of reality. It suggests that existence itself may be probabilistic, not definite, until measured. It reminds us that certainty may be an illusion, and that beneath the surface of our ordinary lives lies a world far stranger than our minds can fully grasp. Wigner's friend. Wigner's friend is a quantum paradox that takes Schrödinger's cat one step further. Imagine that your friend runs the cat experiment. They open the box, look inside, and see whether the cat is alive or dead. For them, the outcome is clear. But for you, standing outside the lab, your friend and the cat are still part of a quantum system. Until you look, they exist in superposition, both having seen a live cat and having seen a dead cat. This creates a disturbing paradox. For your friend, reality has already collapsed into one outcome. But for you, their entire experience is still undecided. Whose reality is the real one? Does observation create truth? And if so, truth for whom? Wigner's friend highlights the unsettling possibility that reality is not absolute but observer-dependent. Different people might experience different realities until they compare notes, and even then, the act of communication becomes part of the quantum collapse. On a deeper level, this paradox challenges the idea of objectivity itself. If reality depends on observation, then truth may not exist out there, independent of minds. It may arise only in the interaction between observer and observed. Wigner's friend paradox reminds us that consciousness and reality may be entangled in ways we barely understand. It leaves us with a haunting question. Is there one reality, or as many realities as there are observers? The quantum suicide paradox. The quantum suicide paradox is a thought experiment that takes Schrödinger's cat and turns it on the observer. Imagine a scientist sets up a deadly quantum experiment, a gun linked to a quantum device. Each time the device measures a particle, there is a 50% chance the gun fires and kills the scientist, and a 50% chance it clicks harmlessly. According to the many worlds interpretation of quantum mechanics, every measurement splits the universe into two branches. In one, the scientist dies. In the other, they live. From the outside perspective, there are countless branches of the universe where the scientist is dead, but from the scientist's own perspective, they never experience their death. In every branch of reality they survive, because consciousness only continues in the versions where the gun does not fire. To them, it seems as if they are immortal, living through an infinite sequence of survivals. The paradox is haunting. It suggests that from the first-person perspective, death might never arrive, only endless survival in stranger and stranger branches of the multiverse. But at the same time, from the third-person view, the scientist certainly dies in most branches. Both truths coexist, depending on perspective. On a deeper level, the quantum suicide paradox raises terrifying and fascinating questions about identity, probability, and existence. Does it mean immortality is real, at least in some sense? Or is it just a trick of interpretation, a way of bending logic until it feels like magic? This paradox reminds us that quantum mechanics doesn't just challenge physics, it challenges our very definition of life and death. The measurement problem. The measurement problem is one of the deepest mysteries in quantum mechanics. It asks, how and why does the act of measurement collapse a wave function into a definite outcome? In the quantum world, particles like electrons or photons exist in superposition. They don't have a definite position, spin, or state until measured. The equations that describe them allow multiple possibilities at once, but when we observe them, we see only one definite result. Where did the other possibilities go? This is the measurement problem. Quantum theory is incredibly accurate at predicting probabilities, but it doesn't explain how probabilities turn into reality. Does observation by a conscious mind collapse the wave function? Does interaction with the environment cause decoherence, making one outcome stick? Or do all outcomes happen, splitting into parallel universes, and we only see one branch? The paradox reveals a gap between theory and reality. The equations describe a ghostly, probabilistic world, but we live in a definite, concrete one. How do the two connect? On a deeper level, the measurement problem asks whether reality exists independently of observation, or whether observation itself is part of reality's construction. It challenges the idea of an objective universe, and hints that consciousness may be woven into the fabric of physics itself. Maxwell's demon is a thought experiment that questions the second law of thermodynamics, which says entropy, disorder, always increases in a closed system. Imagine a tiny demon controlling a trapdoor between two chambers of gas. The demon lets fast-moving, hot molecules pass one way and slow-moving, cold molecules pass the other. Over time, one side of the chamber heats up and the other cools down, seemingly reducing entropy without expending energy. This violates the second law, which says disorder should always rise. So, how could the demon cheat the laws of physics? The paradox forced scientists to reconsider the nature of entropy. Later analysis showed that the demon isn't free. In order to measure molecules and remember their speeds, it must use energy and store information. The cost of the demon's memory cancels out the entropy reduction, saving the second law. But the paradox reveals a deeper connection between energy, information, and computation. It suggests that knowledge itself has physical consequences, and that information is not just abstract, it is tied to the material world. On a philosophical level, Maxwell's demon reminds us that even the most fundamental laws of nature can be challenged by imagination. It also hints at the power and limits of intelligence. Knowing is never free. Every attempt to order the world comes with hidden costs. Loschmidt's paradox challenges the very idea of the arrow of time. In physics, the laws that govern particles, Newton's laws, quantum mechanics, even relativity, are time-symmetric. That means if you ran the equations forward or backward, they would work the same. But in reality, time clearly flows one way. We see eggs crack but never uncrack, glasses shatter but never reassemble. Entropy, the measure of disorder, always increases. So here's the paradox. If the fundamental laws of motion don't prefer a direction, why does entropy rise only in one direction? Why do we experience time as an irreversible flow, when physics says it could just as easily run backward? Ludwig Boltzmann explained entropy statistically. Disorder is simply more probable than order. But Loschmidt pointed out a flaw. If molecules follow reversible laws, then statistically, nothing prevents entropy from decreasing too. If time can be reversed in theory, why doesn't it ever reverse in practice? The paradox forces us to ask whether the arrow of time is real or an illusion. Is time itself flowing, or are we just creatures stuck perceiving one slice of an eternal, symmetric universe? On a deeper level, Loschmidt's paradox reminds us that time may not be what we think. What feels like an unstoppable river may be nothing more than a statistical trick of perspective, a story told by entropy to minds that crave direction. The ultraviolet catastrophe. The ultraviolet catastrophe was one of the great paradoxes of 19th century physics, a problem so severe it helped launch quantum theory. Scientists studying blackbody radiation, the glow of heated objects, used classical physics to predict how energy should spread across different wavelengths of light. Their equations showed that as wavelength got shorter, into the ultraviolet range, energy should skyrocket to infinity. That would mean every heated object should instantly release infinite energy and burn the universe to ash. Clearly, this didn't happen, but according to classical physics, it should. The paradox was resolved by Max Planck, who proposed that energy is not continuous but comes in tiny, discrete packets called quanta. This radical idea, the birth of quantum mechanics, explained why energy levels don't blow up at short wavelengths. The ultraviolet catastrophe is powerful because it shows how paradoxes are not just puzzles but engines of progress. A contradiction between theory and reality forced scientists to abandon centuries of assumptions and enter the strange new world of quantum physics. On a deeper level, this paradox reminds us that the universe is stranger than reason alone can predict. When our models fail catastrophically, it may not be reality that's broken. It may be our understanding. The Poincaré recurrence paradox. The Poincaré recurrence paradox begins with the idea that in a closed finite system, particles move in predictable ways according to physical laws. If the system runs long enough, unimaginably long, the particles must eventually return to almost the exact same configuration they started in. In other words, given infinite time, the universe would repeat itself. This leads to unsettling consequences. If the universe is finite but eternal, then every event, your birth, your thoughts, this very moment, will eventually recur, over and over again, infinitely many times. Reality would not just happen once, but cycle forever, endlessly repeating itself. But here's the paradox. This seems to clash with the second law of thermodynamics, which says entropy always increases. If entropy rises forever, how could the universe ever return to its original low entropy state? The recurrence theorem says it must, but thermodynamics says it cannot. The paradox forces us to ask, is the universe a one-way journey into heat death, or a looping cycle that endlessly repeats? Are we unique, or have we lived these lives before and will again? On a deeper level, the Poincaré recurrence paradox isn't just about physics, it's about meaning. If everything repeats, does anything matter? Or does recurrence give our lives a strange kind of immortality, as every moment echoes across eternity? The Banach-Mazur paradox. The Banach-Mazur paradox is a cousin of the Banach Tarski paradox, and it shows how infinity and geometry can bend our intuition until it breaks. It says that it is possible, using only the rules of set theory and group theory, to take a solid ball in three-dimensional space and cut it into a finite number of strange, non-measurable pieces. Then, by simply rotating and rearranging those pieces, you can reassemble the ball into one that is twice as large as the original. At first glance, this sounds like sorcery. How can you take one finite object and, without adding any matter, produce a larger one? But the paradox comes from the fact that the pieces are not ordinary chunks of matter. They are infinitely complex sets of points that cannot be measured in the usual sense. The Banach-Mazur paradox highlights the deep divide between the mathematical world of infinity and the physical world of atoms. In real life, you could never perform this trick. Matter is made of discrete particles, not infinite point sets. But in mathematics, where infinite divisibility is possible, the paradox holds. On a deeper level, this paradox challenges the idea of volume, size, and measure. It teaches us that the rules of the infinite are not the rules of the finite. What feels impossible in our world may be entirely logical in the abstract realm of mathematics. It's a reminder that infinity is not just bigger than we imagine, it is stranger than we can imagine. The paradox of enrichment comes from ecology, and it asks a troubling question. Can making an environment better for a species actually make it more likely to collapse? Imagine a predator-prey system, like wolves and rabbits. If you enrich the environment for the prey, giving the rabbits more food, more space, more resources, their population will grow rapidly. At first, this looks like a good thing, but as the rabbit population explodes, the wolves have more food too, so their numbers also grow. Soon, the wolves consume the rabbits faster than they can reproduce, driving the rabbits to near extinction. With no prey left, the wolves collapse too. What started as enrichment ends as destruction. This paradox shows that stability in ecosystems is delicate. More abundance does not always mean more sustainability. In fact, too much enrichment can push a system into dangerous oscillations, leading to instability and collapse. On a deeper level, the paradox of enrichment reflects human behavior as well. When societies overuse resources, overproduce, or overstimulate systems, they often create crises instead of stability. More is not always better. Sometimes, it's the path to ruin. The paradox is a sobering reminder that growth without balance is dangerous, and that true sustainability means respecting the limits of systems, not pushing them to extremes. The paradox of vulnerability. The paradox of vulnerability comes from psychology and philosophy, and it asks, why does exposing our weaknesses often make us stronger? At first glance, vulnerability looks like danger. To be vulnerable is to risk rejection, betrayal, or harm. Logic says we should protect ourselves, hide our weaknesses, and shield our hearts. Yet paradoxically, research and lived experience show that vulnerability is the foundation of trust, intimacy, and courage. When we open ourselves to others, even at the risk of pain, we create the possibility of deep connection. A leader who admits uncertainty gains respect. A friend who shares their struggles invites closeness. A person who risks failure in pursuit of a dream may find success that the cautious never reach. The paradox is that strength often comes not from armor, but from openness. By admitting our limits, we invite growth. By exposing our wounds, we allow healing. Vulnerability feels like weakness, but becomes the gateway to resilience. On a deeper level, the paradox of vulnerability reveals something profound about the human condition. We are strongest when we dare to be fragile. It teaches us that perfection is not what binds us together. It is honesty, courage, and the willingness to be seen as we truly are. The hedged philosopher's paradox. The hedged philosopher's paradox explores the difficulty of making absolute statements while trying to protect them with conditions. Imagine a group of philosophers debating a universal claim like, all swans are white. Someone raises the objection that there might be a black swan somewhere, so the philosophers hedge. All swans are white, except for possible exceptions we don't know about. On the surface, this protects the statement from being disproven, but paradoxically, it also drains it of meaning. If every universal claim is wrapped in exceptions, This is always true, unless it isn't. Then philosophy collapses into vagueness. A statement that cannot be disproven is no longer a real claim about reality, but a tautology, a kind of word game. The paradox reveals that in trying too hard to defend truth, we may destroy it. On a deeper level, the hedged philosopher's paradox is about the human fear of being wrong. We hedge our statements to appear safe, but in doing so, we risk saying nothing at all. It teaches us that truth requires courage, the courage to make claims that can, in fact, be challenged. Without that, philosophy, science, and even personal honesty lose their power. The Sorcerer's Apprentice Paradox. The Sorcerer's Apprentice Paradox comes from a famous story retold by Goethe and later popularized by Disney's Fantasia. An apprentice, eager to avoid hard work, enchants a broom to fetch water for him. At first, it works beautifully, but soon, the broom keeps fetching water endlessly, flooding the house. The apprentice cannot stop it, because he doesn't know the counterspell. The power that was supposed to save him, effort becomes a disaster. The paradox here is the danger of power without wisdom. Magic, technology, or knowledge in the wrong hands can spiral out of control. What begins as help can become harm if we lack the understanding to manage it. In modern times, this paradox resonates with artificial intelligence, automation, and even social media. We create tools to serve us, but those tools can grow beyond our control, creating unintended consequences. Like the apprentice, humanity risks being overwhelmed by forces it unleashed without mastering. On a deeper level, the Sorcerer's Apprentice Paradox is not just about tools, but about human ambition. We long for shortcuts, for control without responsibility. The paradox reminds us that true mastery requires discipline, patience, and humility. Without them, even our greatest powers may turn against us. The paradox of inquiry revisited. The paradox of inquiry, also known as Menno's paradox, deserves another look because of its haunting simplicity. It asks, how can we search for knowledge if we don't already know what we're searching for? If you know it, you don't need to search. If you don't know it, how would you recognize it when you found it? This paradox strikes at the core of learning. It suggests that inquiry itself is impossible, a logical trap that makes discovery seem out of reach. Yet, human beings clearly do discover new truths. How? Plato's answer was the theory of recollection, the idea that learning is really remembering what the soul already knows. But even outside Plato, the paradox reminds us of the mystery of discovery. How do scientists recognize patterns in data they've never seen? How do artists create beauty they've never imagined before? How do ordinary people realize truths about themselves that were hidden all along? Somehow, humans leap beyond ignorance into understanding. On a deeper level, the paradox of inquiry reveals that knowledge is not only about logic, but about intuition, creativity, and the spark of recognition. We don't begin with nothing. We begin with questions, hunches, and inklings that guide us forward. The paradox reminds us that inquiry is not impossible. It is miraculous. The Barber Paradox, revisited. The Barber Paradox is a classic from Bertrand Russell, and since it began our list, it deserves a deeper revisiting at the end. Imagine a barber in a town who shaves every man who does not shave himself. The question is, does the barber shave himself? If he shaves himself, then he falls into the category of men who shave themselves, so he shouldn't shave himself. But if he doesn't shave himself, then he falls into the category of men who must be shaved by the barber, which means he must shave himself. Either way, the definition of the barber collapses. Russell created this paradox to illustrate a problem in set theory, the idea of sets that contain themselves. If you define the set of all sets that do not contain themselves, do you include that set in itself or not? Just like the barber, the definition implodes. On a deeper level, the Barber paradox is not just about logic. It is about the danger of self-reference. When definitions fold back on themselves, contradictions emerge. It teaches us that even simple-sounding rules can create impossibilities when they loop inward. The Barber paradox reminds us of the fragility of language and systems. It warns that even our most precise tools, logic, mathematics, words, can tie themselves in knots when asked to define too much. And yet, in those knots, paradoxes are born, puzzles that stretch our minds and reveal the limits of thought itself.